go. There we go. Usually works. So. It's coming? There we go. Okay. Excellent. Is it good?
Your slide is not show all your transcript.
Oh, okay.
Maybe you should restart the PowerPoint.
Yeah. Let me try again.
It's fine, just not good.
Is it good? Okay. Okay. It shows up on your screen.
I will switch it.
Yeah, okay. Thank you.
Top stuff.
Yeah.
Is it fine now?
Yeah, it's fine now.
Okay, let's start.
Yeah.
Okay, let's start. So, hello everyone. Welcome to Public Programming and Announce 2. I'm your citing chair, Xin, from Peking University. So our first talk is by Long from College Mellon University. And the title is Programmable MCMC with soundly composed guided programs.
Hello, my name is Long Pham. I'm a PhD student from Carnegie Mellon University, working with Dee from Peking University and Firas and Yang from Carnegie Mellon. Today we present Programmable MCMC with soundly composed guided programs. So to set the stage, let me first introduce probabilistic programming. The user first writes a probabilistic model, which is a joint distribution of two random variables, theta and y, as a program. And this model program may contain conditional statements and loops. Here we have two random variables, theta and y. Theta is a latent variable, which we want to infer, and y is an observed variable for which observed data will become available. Next, the user collects observed data, D, and use it to compute the posterior distribution, which is given by Bayes' rule on the slide. The denominator of the right-hand side involves an integral of the space of theta. Because this space is usually high-dimensional, computing this integral is intractable. So instead, in practice, we run a sampling-based inference algorithm, such as Markov chain Monte Carlo, or MCMC for short. It works by running a Markov chain that is carefully designed to converge to the target distribution. We start with some state, theta 0, on the slide, and we propose a new state, theta 1 star, by drawing a sample from a proposal distribution Q. We then probabilistically jump to this state with some probability, otherwise we stay in the old state, and we repeat this step many times. And the collection of samples drawn from this Markov chain serves as an approximation of the target distribution. As a running example throughout this presentation, I will next introduce Bayesian polynomial regression. The model program works as follows. It first probabilistically generates the polynomial degree D by sampling it from a categorical distribution with 3 buckets. So the degree in this example is either 0, 1, or 2. Next, the model probabilistically generates a constant coefficient, C0, for the polynomial, and depending on the value of the degree, it additionally generates linear and quadratic coefficients, C0, C1 and C2, if necessary. So the set of random variables generated in this model depends on which execution path we take in the model. And lastly, the model generates observed variable y around the polynomial function that we just generated by adding some random noise. So if we run this probabilistic model, then we obtain these prior polynomials with various degrees ranging between 0 and 2. And the goal of Bayesian inference in this example is to answer this question. Given the observed data for y, what are the likely degree and coefficients of polynomials that generate the observed data? So, for example, given these red points on the slide, our goal is to infer or approximate a posterior distribution of polynomials like these black curves on the slide that likely have generated the red points. Traditional probabilistic programming languages use a generic inference algorithm that is applicable to all Bayesian inference problems, but it may perform poorly by failing to converge to the target distribution quickly enough. This is the result of running a generic inference algorithm in our running example of Bayesian polynomial regression. For this plot, we draw 50 posterior samples of polynomials. And as you can see, many of them overlap. So there's little variance within these 50 posterior samples. And it means that the generic inference algorithm does not effectively explore the space of posterior samples. To this end, modern PPL such as Gen and Pyro support programmable inference where the inference algorithm is customized by a user-written program called a guide program. Specifically for MCMC, this guide program customizes a proposal distribution used in a Markov chain. In this work, we study a variant of MCMC called multiple block metropolis hastings, or BMH for short, which samples random variables block by block. So to give you an example, let's say in Bayesian polynomial regression, the user splits the set of random variables into 4 blocks, each of which contains exactly a single random variable, namely D, which is a polynomial degree, and the 3 coefficients, C0 up to C2. Additionally, the user specifies the proposal distributions for each block. To customize the inference algorithm this way, the user writes 4 guide programs, 1 for each block. In BMH, we run these guide programs one by one, where in each guide or each block, we sample those random variables in the block while keeping other random variables unchanged. So back to our example, let's focus on the first guide, GD, for the polynomial degree D. It first samples the random variable D, and for all the other existing random variables, it simply reuses old values. And after running this guide, we obtain the trace sigma 1 star, which stores all the values of the random variables. And then we perform the so-called MH update, where we probabilistically select the newly proposed state. Otherwise, we stay in the old one. And then we pass on this trace to the next guide, and then repeat the same step for the remaining guides. And this is a result of running BMH on our example. As you can see, this time we now have more variance within the 50 posterior samples generated by BMH as compared to the generic inference algorithm from the previous slide. So by customizing the inference algorithm, specifically by splitting the latent variables into blocks and sampling them block by block, we obtain more accurate posterior samples, also more quickly. In order for BMH to converge to the target distribution, it should satisfy the sufficient soundness condition that the model and guide must have the same support. For instance, in a guide program for the quadratic coefficient C2 in our running example, let's say we replace a normal distribution where the support contains all reals with a gamma distribution where the support not only contains non-negative reals. Then it results in unsound BMH because now the guide is unable to sample negative values for the quadratic coefficient C2. And the result of this unsound BMH is on the slide, where clearly the posterior distribution of polynomials does not fit the red points, namely the observed data. So in this work, our contribution is the following. We developed a type-based framework for statically verifying that the model and guide have the same support for BMH, which is a key soundness condition. And this is checking this condition statically is challenging because the set of random variables depends on which execution path we take in the model and guide programs. So now that we have motivated the static analysis of BMH to check its soundness, next I will describe our 3 contributions, namely formulation of BMH, polynomial time decidability of structural equality, and coverage checking. And at the end, I will briefly discuss our implementation and evaluation. So for our first contribution, we formulated BMH as a sequential composition of guide programs, as illustrated on the slide. So for our example of Bayesian polynomial regression, because we have 4 blocks, we also have 4 guide programs in the bottom row, so GD up to G of C of 2, and each guide communicates with a model program M. So this is the formulation we use to model BMH. And the communication between M and G is done by message passing. Specifically, this guide, so let's focus on the first guide, GD. So it takes as input the odd trace, sigma 0, which stores all the odd samples of all random variables. GD then draws a sample for the random variable D and sends this sample to the model program M. And when we reach a conditional statement in the program, it is the model's responsibility to decide which branch to take, and this branch selection is sent back to the guide. And this communication continues between the model and guide until they terminate. And once we obtain a trace after running the guide G, then we perform the image update, where we probabilistically select the next trace to be passed on to the next guide. And then we repeat the same step for the remaining guides. And this communication protocol between the guide and protocol, the communication protocol between the guide and model is described by this guide type on the slide. So here N3, which denotes the distribution type of the random variable D, captures the support of the distribution from which we draw a sample for this random variable. Because the polynomial degree was generated from a categorical distribution with 3 buckets, it's the corresponding distribution type is N3, where the subscript 3 means that we have 3 buckets in the categorical distribution. And the ampersand in the guide type means that we have a conditional statement. And if we pick the first branch, then the guide terminates because there's nothing else to sample for. So this termination is denoted by the guide type 1. Otherwise, in the second branch, the model and guide continue their communication to additionally sample for the linear and quadratic coefficients. So in this formulation of BMH, a key soundness ingredient is that the model and guide must have an equal guide type. Because otherwise, the communication between the model and guide will fail. And guide types in general can be context-free types, which are types indexed by type parameters. An example of a context-free type is on the slide, where T is a type name and X is a type variable. So the intuition of the guide type Tx is that we first run a protocol T, followed by some continuation captured by the variable X. And if you look at the definition on the right-hand side, it says that we first draw a sample with the distribution type R, followed by a choice between 2 branches. So that's denoted by the ampersand. And if we pick the first branch, then we simply proceed with the continuation protocol X. Otherwise, in the second branch, we run T of X. And the intuition is that we run the protocol T twice, sequentially, followed by X. And guide types may have infinite state spaces because, for example, on the slide, as we walk through the type and unfold its definition, we get Tx and 2 T's of X and 3 T's followed by X and so on. So to check the structural type equality of guide types, we cannot simply exhaustively explore the state spaces because they can be infinite. So our second contribution in this work is to prove that structural guide type equality is decidable in polynomial time. To show it, we first translate guide types to context-free processes, which are basically context-free grammars viewed as processes. Next, we require that the norms, namely the number of steps to reach termination from any state in the guide type, to be finite. And this is a sensible requirement in the context of probabilistic programming because we expect probabilistic programs to eventually terminate and return finitely many samples instead of running forever as in networks. And lastly, we appeal to the theorem proved by Hirschfeld and his colleagues in 1994 that the bisimilarity of two context-free processes with finite norms is decidable in polynomial time. And thanks to our translation from guide types to context-free processes, it also means that the structural guide type equality is also decidable in polynomial time. So next, I will talk about coverage checking. So given a sequential composition of guide programs, every random variable must be covered. That is, it must be sampled freshly by some guide program in the sequential composition, regardless of what execution path we take. Because otherwise, if some random variable is never sampled by any guide in the sequential composition, then the model and guide will have different supports for that particular random variable. And a more formal problem statement of checking coverage of random variable is the following. Let's say we are given an arbitrary initial trace sigma 0 and an arbitrary final trace sigma b. So pictorially, we are given a sequential composition of guides, and we fix an arbitrary initial and final traces. Then the question is, do there exist intermediate traces, sigma 1 to sigma b1, sigma b minus 1, such that for each I, the guide gi can generate the desired trace, sigma I, using the previous trace, sigma I minus 1. And in the interest of time, I will only give a high-level idea of the coverage checking algorithm. But the basic idea is that we first annotate guide types with coverage annotations to track which random variables have been sampled, using subscripts U and C to indicate whether a given random variable is covered or uncovered. And then, given a sequential composition of guides, we walk through them one by one to update the coverage annotations whenever random variables are freshly sampled in the current guide. And then at the end, we check the coverage annotations of all random variables to see whether they are all covered. And if that is the case, it means that all random variables are freshly sampled at some point during the sequential composition, which means that the BMH is sound. So lastly, let me briefly talk about our implementation evaluation. So we implemented an algorithm for checking structural type equality and embedded it into type inference. For the benchmarks, so this is the table which is available on the paper with more details. But for the benchmarks, we reuse the benchmark programs from the previous work by D. Wang and also his colleagues from PLDI 2021. And we split each benchmark into multiple blocks. So we basically use BMH for each benchmark. And then our evaluation shows that some BMH benchmarks require structural guide type equality instead of simple, naive, syntactic type equality to be able to infer types. And we also implemented an algorithm for coverage checking, and our evaluation shows that our algorithm is effective for those benchmarks where the state spaces of guide types is finite. But for those benchmarks where the guide types may have, or the guide types have infinite state spaces, then our coverage checking algorithm can return false negative because the algorithm is sound but incomplete. And for more details, please look at the paper. So in conclusion, we made 3 contributions in this work. First, we formulated BMH, which samples random variables block by block in the guide-based framework of programmable inference as a sequential composition of guide programs. We additionally proved polynomial time decidability of structural type equality for guide types, which in general can be context-free and hence have infinite spaces. And lastly, we developed an algorithm for checking coverage of random variables to statically verify that each random variable has been freshly sampled by some guide in the sequential composition, which is a key soundness condition for BMH. Thank you.
So if a program fails your verification, what kind of feedback you give to your programmer to fix the program?
So we didn't really investigate the kind of error messages that we can return to the user, but okay. So first of all, for equality checking of types, so let's say the guide and model have unequal types, then we can return some intermediate sort of states of the algorithm that we use to check type equality, and those intermediate states may be useful to the user. But back to your question, we don't really consider sort of we don't aim to return useful error messages. I think that would be the future work.
Yeah, I would love to see it. Thank you very much.
Yeah, thank you.
Okay, let's thank the speaker again.
Sorry?
No need to check the screen. I will switch it out.
Ah, all right. Yeah, I think then we can.
Just stay close to the mic. You should. I cannot see your slide on the screen.
Sorry?
I cannot see your slide on the screen. Did you start to project it?
Can you do it? I don't know what I tested just before and.
There is no slide on the screen.
Let's see what happens. So
I tested before the talk, it was working fine. So,
should we disconnect it and reconnect and see?
yeah, let's show you.
No need to reconnect. The display output is good, but the slide have not been played yet.
Oh, if you just played it, it'll be fine. I see your point. Is it okay? Okay.
All right.
Okay, everyone. Our next speaker is Georgia from Singapore Management University. And he will talk about quantitative bounds on resource usage of probabilistic programs. Please, Georgia.
Hi. Thank you very much for the introduction, and thank you everybody for coming. So yes, I'm George Zhikovic, and this is joint work with Krishnendu Chatterjee, Amir Gokharshadi, and Tobias Megendorfer. So I don't really think that this slide is necessary for this session, but just to set up the stage. So probabilistic programs are classical programs extended with sampling instructions. In static analysis, we often also extend them with non-determinism in order to allow modeling on user inputs or program abstractions, and this is what we do in our work as well. So this allows us to model a range of applications in which probabilistic systems arise, such as randomized algorithms, cryptographic and security protocols, and so on. What we do not consider in this work is programs with conditioning, which are typically used in Bayesian inference and Bayesian reasoning. So we treat probabilistic programs more as randomized algorithms. Now, cost or resource analysis is a static analysis concerned with computing bounds on cost or resource usage of a program. It's a prominent static analysis both in the non-probabilistic and probabilistic programming setting because it has many applications, for instance, computing bounds on program runtime, memory usage, energy consumption, and so on. And typically, in static cost analysis, we extend programs with a stick construct syntax, which basically indicates that the cost is incurred at some step of a program and the value of the cost is equal to the value of the expression in the brackets. Now, cost analysis problem in probabilistic programs is arguably more challenging compared to the non-probabilistic version. Because unlike in non-probabilistic programs where on each input we have a single output, probabilistic programs produce a probability distribution over the set of all of their runs. So the question is, how do we define the cost analysis problem? First of all, for a single run, we can define its cost simply as a sum of all incurred costs at each step. In case of a non-terminating run, we need to take a limit superior, of course. And then there are two variants of the cost analysis problem that have been considered in the literature. The first is concerned with computing expectation bounds. So we're interested in computing an upper bound on the expected value of cost usage. In the case of programs with non-determinism, of course, subject to every possible scheduler used to resolve non-determinism. So this is more like aggregated information about all program runs. Tail-bound analysis problem is maybe a bit more informative because given a threshold, we're interested in computing a probability that the cost exceeds the threshold. So with different values of this threshold, we can get a more fine-grained information about how cost is distributed. And in this work, we will consider both of these problems. Now, recent years have seen a lot of developments, significant developments in cost analysis for probabilistic programs, but in our work, we observe a few limitations in the sense of what classes of probabilistic programs existing automated methods are applicable to. So in the context of expectation bounds, existing methods assume mostly that program is almost surely terminating and that in addition it satisfies at least one of the following assumptions. So either all costs need to be non-negative or variable values updates have to be bounded in the sense that there exists some global bound on how much the value of each variable can be changed by some variable assignment. Or they consider there are methods, for instance, based on exact inference, which do not impose these assumptions but require that all loops in a program are statically bounded. When you talk about tail bounds, existing methods in addition to these assumptions also require that all programs have finite expected cost usage. This is because they first typically derive a bound either on the expected value of cost or on some higher moment, and then use this information in order to derive tail bounds. Now, our goal in this work is to basically try to close this gap and to get cost analysis methods that are applicable to broader classes of programs, and to see which of these assumptions we can relax a bit. Of course, theoretically, this is a very interesting problem, but one might ask, okay, are there any interesting practical applications of probabilistic programs where, programs that do not satisfy some of these assumptions arise? And in our work, we actually identify a few interesting applications, both for expectation and for tail bounds. So in blockchain protocols, which can be modeled as probabilistic programs, there are several interesting analyses about attacks on different blockchain protocols that can be modeled as probabilistic programs, and designing attacks corresponds to basically solving the cost analysis problem. So both for expectation and for tail bounds, we observed some interesting examples, and I will not go into the details. You can look at the paper where basically we find programs that are not almost surely terminating in some cases, or they are almost surely terminating, but they don't have bounded variable updates or have both positive and negative costs. So existing methods for cost analysis are not applicable to them. Another interesting class of examples is programs that do not terminate almost surely, but we want to derive tail bounds on their termination time. So termination time can be treated as cost analysis, right? We have unit cost at every execution step. Expected cost usage in non-almost surely terminating programs is infinite, so existing methods are not applicable, but we still might be interested in deriving bounds on, for instance, termination time exceeding 1,000. And this is something that is another interesting application. All right. So our contributions in this work are as follows. So we try to relax some of these assumptions, and we propose new proof rules for expectation and for tail bounds. Our proof rule for expectation bounds builds on prior work on cost supermartingales, where we showed that cost supermartingales can be are actually applicable to a broader class of programs that was initially shown, actually relaxing these three assumptions. For tail bounds, cost supermartingales alone are no longer applicable if we have infinite expected cost usage, because existence of a cost supermartingale still implies finite expected cost usage. So we actually couple cost supermartingales with something called stochastic invariance in order to obtain a proof rule for tail bounds that is applicable even to programs with infinite expected cost usage. Then we showed that computing instances of these proof rules, so both for expectation and for tail bounds, can be fully automated in programs with linear or with polynomial arithmetic expressions. And then finally, we implemented a prototype and showed that some of these interesting applications that we identified can be solved using our new proof rules. So I won't have much time to go into the technical details, so I will just give you a high-level overview, basically, of what we have done. And if you have any questions, I'm happy to discuss either after the talk or during a coffee break. So let's start with expectation bounds. So as I've mentioned, our new proof rule essentially relaxes conditions in which cost supermartingales are applicable. So cost supermartingales were introduced in this PLDI 2019 paper. And intuitively, for those of you familiar with the non-probabilistic cost analysis literature, they can be viewed as a stochastic version of potential functions. So they are functions which map program states to some real values, which are required to decrease at every one-step execution of a program, decrease in expected value at least by the expected incurred cost. So in expectation, the decrease of the cost supermartingale value matches the increase in the incurred cost. And finally, we require that this function is non-negative upon termination. It was showed in this paper that if a program is almost surely terminating and has either non-negative costs or bounded variable updates, cost supermartingales provide a soundproof rule for expectation bounds in the sense that the value of the cost supermartingale at the initial state of a program evaluates an upper bound on expected cost usage. So unlike potential functions, which are sound even without these assumptions, cost supermartingales are actually not sound in the general case, but with these assumptions, they do become sound. Now, what we did in our work, we basically showed that the conditions from the previous slide can be replaced by a different condition, which we call lower bounded total cost condition. So what we require is that there exists some global bound k, which can be negative, on the total cost usage along every run. So basically, the costs can be positive, negative, the cost can increase or decrease, but along the whole run, the total cost never falls below this value k. And then what we show is that basically we can remove all these assumptions, including almost sure termination, and only if we require lower bounded total cost condition, cost supermartingale still remains sound for deriving expectation bounds. So I've mentioned that we had some examples where basically prior proof rules could not be applied. So if you look at one of these, which is this Bitcoin pool mining, so again, I will not go into the details, but it turns out that this program does satisfy lower bounded total cost condition, but it does not satisfy the previous conditions. So it still admits a cost supermartingale, but because the two conditions are not satisfied, prior proof rules could not derive expectation bounds here, whereas now we are able to actually, our algorithm automatically checks that this program indeed satisfies lower bounded total cost condition, and we are able to derive expectation bounds in this example. So just to comment a bit on the relation to other conditions. So non-negative costs, of course, naturally imply lower bounded total cost condition because 0 is a lower bound. However, bounded variable updates, the set of programs that satisfy this condition, are neither a subset nor a superset of the lower bounded total costs. So what we did is we didn't really completely generalize the applicability of cost supermartingales. Rather, we proposed a different condition which encapsulates a new class of programs to which prior variant of cost supermartingales was not applicable. But I think it would be a very interesting direction of future work to think of a condition which relaxes both of these and ultimately is applicable in all, let's say, settings. All right, that's about expectation bounds. Now about tail bounds. So as I've mentioned, cost supermartingales alone can be used to derive bounds in programs with finite expected cost usage, but we want to target programs with infinite expected cost usage, such as tail bounds on termination time of not almost surely terminating programs. So in this case, we couple them with something called stochastic invariance. Now, the formal proof rule I leave to the paper. I will give you an intuition behind the proof rule. So if you look at this program on the left, it is not almost surely terminating because of this boxed part. So without the boxed part, this would simply be a one-dimensional random walk, continuous, and it would terminate with probability 1, and actually existing methods for cost analysis would very easily handle it. But because of this condition, if x is at least 200, then program can actually diverge. This program does not terminate almost surely. Now, we can think of this as a bad part. And basically, if we are able to automatically identify this bad part and to derive a bound on the probability of ever going there, intuitively, we should be able to derive tail bounds for this example. And this is essentially the key idea behind our new proof rule. So we basically automatically identify this bad part. We compute an upper bound of the probability of ever going to the bad part. And then we consider the modified program, which terminates once we go to the bad part, and we derive tail bound for this program. And we show that basically just summing up these two probabilities gives you a sound tail bound for the original program. How do we go about identifying this bad part? Well, we use prior work on stochastic invariance. This is actually based on our prior work, Popple 2017 paper, where basically a stochastic invariant is a set of states together with an upper bound on the probability of ever leaving the state. So basically a bad part is a complement of a stochastic invariant. And in prior work, we actually developed algorithms for computing these stochastic invariants, and we can utilize them in combination with cost supermartingales in order to derive tail bounds. Now, About automation, so we showed that if all arithmetic expressions in programs are either linear or polynomial expressions over program variables, we can automate the computation of instances of both proof rules. Our automation is based on template-based synthesis. So basically, we will leverage existing algorithms for template-based synthesis of cost supermartingales and of stochastic invariants, and basically we'll synthesize them simultaneously. So how this works, we fix symbolic polynomial templates. So polynomial expressions representing stochastic invariant, this probability bound, and also cost supermartingales. Then we collect a system of constraints over the symbolic template variables that together encode that this is indeed a correct stochastic invariant, correct cost supermartingale. For this, we really just reuse existing methods for template-based synthesis of these objects, and we just combine constraints together. We also derive constraints that the program needs to satisfy in order for the lower bounded total cost condition to hold within this modified part of the program. And then finally, a constraint. So this is coming from our proof rule, this bound with this tail bound that we need to derive. Resulting system of constraints is a bit complicated because it contains quantifier alternation, which is hard to solve. So we also have a simplification step, which basically is sound and semi-complete and translates these constraints to a system of constraints which is purely existentially quantified and has only polynomial constraints. And this can be solved by using an off-the-shelf SMT solver, and we get an algorithm whose runtime is in p-space. Finally, we implemented a prototype of our method, and we evaluated it on some of these examples that prior methods could not handle, but we also compared at least expectation bounds to other methods that exist. Oops, yeah. So for expectation bounds, we compared to two methods. So first, we compared to the PLDI 2019 paper, which introduced cost supermartingales. Basically, we want to check, okay, there are examples that we can handle, but there are also these other conditions, and as I've mentioned, our condition does not subsume them. So the question is, are there examples that the prior method can handle and we cannot? And we also compared against another prior work which considered non-negative costs. So the new class of programs that do not satisfy conditions of prior methods, of course, they're not applicable, but at least in these applications that we identified, we were able to handle them. For programs with no negative rewards, both us and both the baselines were able to handle all the examples. And this is to show that basically even automatically checking this lower bounded total cost condition does not lead to compromised runtime. And then finally, on examples that satisfy bounded variable updates, indeed there are examples where a method is not applicable. So these programs do not satisfy lower bounded total cost condition. This is something that we check by inspection. So as I've mentioned, it will be interesting direction of future work to think of a relaxation of both conditions, which would still make cost supermartingales sound. For tail bounds, we considered programs with infinite expected cost usage, so there is no baseline to compare against because no other method, to the best of our knowledge, is applicable. So we considered some of these examples that we identified, and we also considered benchmarks from the literature on probabilistic termination analysis. So these are programs that do not terminate with probability 1, therefore have infinite expected runtime, and we wanted to derive tail bounds on the runtime. And we were able to do this at good runtimes, mostly being in order of a few seconds, which is in line with the state of the art. All right, so to conclude, in this work, we present new proof rule for expectation bounds and for tail bounds in probabilistic programs. Our proof rule on expectation bounds is based on cost supermartingales and basically shows that they're applicable in the more general setting that was known before, relaxing some of these assumptions of the prior work. For tail bounds, our proof rule is based on cost supermartingales and stochastic invariants. We presented fully automated algorithms for computing instances of these proof rules and therefore deriving expectation and tail bounds in programs with linear or polynomial arithmetic. And then finally, we implemented a prototype of our method and demonstrated that it can tackle some examples that prior methods could not tackle at runtimes that are comparable to state of the art. I'll be happy to take any questions, and thank you for your attention.
Thank you. I really enjoyed your talk. I was wondering this non-negativity condition. How do you check this one, roughly?
So we basically introduce a variable to track cost usage. And we basically want to synthesize, using template-based synthesis, an invariant which shows that this value never goes below some symbolic constant that we fix. So it's another, we introduced a symbolic variable which should act as a lower bound. Of course, it's real valued. And we just ensure that along no point in the program, this cost variable that tracks the total incurred cost goes below this symbolic variable.
Thank you. So if the condition doesn't hold, but you still run your algorithm, does it fail or does it simply give a wrong result?
So our algorithm will automatically impose this lower bounded total cost condition. So it will never return answer yes if the lower bounded total cost condition has been verified. Has not been verified.
I see. So the verification step is also part of your algorithm.
Yes.
Like you need to first verify that the condition holds.
Yes, so we actually, here in constraint collection, we also collect constraints that ensure that the program satisfies the lower bounded total cost condition.
Okay, thank you.
There's no more question. Let's thank the speaker again.
Thank you.
Okay,
All right.
sorry for the wait. Our next speaker is Alejandro from Chalmers University of Technology. And he will talk about sensitivity by parametricity.
All right, thanks. Sorry for the delay. So this talk is in the context of data privacy, specifically on differential privacy. Differential privacy is a new golden standard for data privacy, and let me give you a quick intuition. We have a data set with personal information. You can imagine that every row belongs to someone's private information. We run a randomized query and we get a result. Differential privacy says that if you choose any of the people in the data set and you remove it, and you run again the randomized query, you will get a result. The probability to get the same result as when you run it with the first data set is pretty close. It's like, and that closeness is related by this parameter epsilon. And in that way, the system kind of behave almost similar if in the data set D1 and D2. Therefore, we are protecting the privacy of any individual. This is kind of the intuition. But how do we create these randomized queries? Well, I will show you one way to do it, which is called the Laplace mechanism. And it's like to create a randomized query, just get a normal query, like this one, how many people earns more than 60K, and just add some noise. So you get the result of the original query, and you add some noise. And the noise is drawn from the Laplace distribution, centered in 0, with an scale sensitivity over epsilon. The scale is what tells you how pointy the Laplace distribution is. Sensitivity is how much, if I change the input of the query, how much the output changes. And most of the differential privacy systems, they have baked-in queries, type of queries, with the corresponding sensitivity, right? That's okay. That's okay, but has a limited the type of analysis you can do. In this work, the motivation is like we want users to write queries and automatically compute the sensitivity, so therefore being more expressive. And let me be more formal now, what I mean by sensitivity. And this is a definition we're going to use. We have a function that goes from A to B, so we have two metric spaces with distant functions in A and B. And we say that a function is k-sensitive if the input distance is at most n, the output distance is at most k times n. Okay? So that means that the output might increase the input distance at most by k. This is what it says. All right, are you warm up for this? Okay, let's see this function. This function is add 42 that takes x and just add 42 to it. And the specs metric is integers and the distance between integers. What is the sensitivity of that function? All right, let's run one test. Yeah, we say like we provide the input 10 and 11, they're at distant 1, the output is at 52, 53, right? So the output is at distant 1. So the sensitivity, therefore, is 1. So there are some more examples there. There is another example, for example, twice. This like multiply x by 2. And if we try this, the sensitivity here is going to be a little bit different. It's going to be 2. You can see here, for example, you give the input 10 and 11 is distance 1, and the output is 20 and 22. The distance is 2. Okay, so increases the input distance by a factor of 2. Okay, the sensitivity therefore is 2. Right, these are pretty simple functions, right? What about these ones? Sort, map, sum, append. What is the sensitivity of these functions? That's a complicated thing, right? And the question is like, can we compute in an automatic way the sensitivity of these functions? And the answer is yes, we can. But you can use the system called FAS, which is kind of the pioneer system in this area, where you can write functions and check for the sensitivity of them. But then you need to embrace linear types. Sometimes dependent linear types, sometimes modal types. And they're very complicated concepts, at least for myself, for me, right? So the message on this talk is like, you don't need any of that. I'm going to show you how to do this. Write user-defined functions and automatically compute the sensitivity, right? Just using two things. Parametric polymorphism, so having for alls in your types, and having type constraints, which is type constraint is a way to restrict the for all. When you say for all A, it's not any type A, it's any type A that fulfills certain conditions, okay? And this is the main idea of the paper. It's like, let's do distance calculations at the type level. This is kind of the main idea. And for that, we're going to introduce this type called rel, that when you see something of type rel D of A, It means you should think as having two values that they are at distance at most d. Okay? Once you have that, then we can start writing functions using this type. For example, this add42 that I showed before. Now we can write it using the rel type. And you can see here that add42 goes from rel d of int to rel d of int. And it uses some special symbols here, because to construct programs with the type real, you need a domain-specific language. And this is called SPAR. And this is the interface. The thing I want to show you here is like two things. It's like you see that there are some calculations at the type level about distances, right? And here, to be technically precise, we have numbers, and then we have data structures like pairs and vectors. And when you start dealing with them, you need to start thinking about norms, like vector norms, to compute distances, right? And what I'm showing here is using only the L1 norm, which is defined like this. If you don't know what, it doesn't matter, just to be precise. But we support other norms. And this is kind of the inside. We introduce a type synonym that says a function has sensitivity k, a function that goes from a to b. If the function, you can type it like that. It takes a rel d of a and returns rel k times d of b for all d. That's where the parametricity comes into play. If you can type check a function like that, it has sensitivity k. And you can see the formal definition that I gave you and the type that you see there are pretty close. Okay, this is the main insight. This is where parametricity comes into play. All right, so for example, the function that we wrote before, this is the type. If we use the type synonym now and type checks, has sensitivity 1. Okay? And this was the question I gave you before, the sensitivity of these advanced functions, right? And then you can see then that source has sensitivity 1. These are functions working on vectors of fixed length, okay? Map has sensitivity k, the function that you're mapping on has sensitivity k, and so on and so forth. All right, let me connect this back to differential privacy, because we started with differential privacy. So this is implementation of the Laplace mechanism. This mechanism I show you that generates queries that fulfill differential privacy. And here we can see that this function takes data sets which differ in one row. It's at distance 1. Right? It takes a function with sensitivity sen, a function that goes from the data set and generate a number. And it produces a differential privacy query which we assert on given epsilon. Here the epsilon is not that standard, because epsilon could be any real number, but Haskell doesn't have, at the type level, doesn't deal with real numbers, so we are using fractions, rationals, okay? So but it's a small detail. All right, so what advantages and limitations do we have? We support different metrics. I show you that if we deal with complex data structure like pairs and vectors, you need to choose norms. I use L1 norm, but there's another one called L infinite, and we can support it. We cannot support L2 norm, because for the L2 norm, if you're familiar with that, you need to do a square root and and a power of 2. And the Haskell system is not strong enough for that. We implement advanced non-trivial differential privacy algorithms like CDF, histograms, or k-means. It's not my intention to you understand the type signature, right? Just to give you a feeling that the things that we can write using our technique. And on top of that, we can compute the sensitivity of advanced functions, generic advanced functions like folds, right? Where the fold is like, you fold over a list with a function with an arbitrary sensitivity, okay? Things that FAS cannot support, but dfas does. dfas is a dependent version of FAS. And we implement all of that in 500 lines of code, okay? Okay, this is great, but is it sound? Why we just like, just hacking? And for that, in the paper you can find the formalization of the DSL SPAR, we call lambda SPAR. It's a model of the DSL. And we have types. We model the types in the calculus. Then we give semantics to a language based on logical relation. And then we prove the fundamental lemma of logical relations. And then finally, using that lemma, we show that if a function has the type for all d, rel d of A into rel k times d of B, has sensitivity k. Okay? So, all right. Some related work. So, you know, the initial motivation for this work was the work of FAST. So we encode all the examples that FAST does to compute sensitivity of functions. We encode it in a SPAR. And then the closest word to us is Solo from OOPSLA 2022, while they use polymorphism to compute sensitivity, right? And you will say, well, but I mean, yeah, you are doing the same thing. Well, not quite, because we use polymorphism in a different way. Yeah, you can see some difference there. For example, they need to assume the sensitivity of any higher order function. I should show you that we compute the sensitivity of map, which is a higher order function, right? And one of the main differences, like their calculus for the guarantees is monomorphic, while ours support polymorphism, right? And actually, we found a bug in the fault primitive, which is the only primitive of recursion. Of course, we communicate with them, and then they are aware of this. All right. To wrap up, yeah, the main message for you is like you don't need to use linear types to compute sensitivity of functions. If you have parametricity, polymorphism, and type constraints, then you are fine. So you can implement this in mainstream functional languages like Haskell, right? Yeah. So we have good sets of expressivity. I show you that we have implements many of the examples of FAST, as well as we implement advanced differential privacy algorithms. Yeah, and what I'm really interested in is like the next step. Where do we go next? So we found like there are some limitations in the Haskell type system, but you know we have dependent types that they also enjoy parametricity properties, right? So what can we do there that we cannot do here, or what things can be more natural doing in a dependent type language that here we are suffering a little bit of doing. Okay. So with that, I thank for your attention. There where you have the code, and I will be leaving after lunch. So if you want to chat more about this, just talk to Elizabeth. Elizabeth will be around here. Raise your hand. Yeah. So she will be here, and she will love to talk about this. Thank you very much.
Thanks. Thank you. I really like the talk. So I don't work on types, but my understanding is that like this Lipschitz continuity stuff is like a hyper property, but then you denote the signature of your functions as like rel d to rel d. But the rel d things, like, I mean, that's not describing like the object that the function acts on. It's describing like sort of if you were to lift it over a pair, what would happen. So maybe
that's right. Yeah.
Yeah. So I guess my question is like, in your opinion, then like, what is a type? Maybe that's a confused question, but I guess I was surprised to see things done this way. I don't work in types, so I don't know if it's standard, but I wonder if you could like tell us whether this has anything to tell us about like what a type is, because it seems like it's a somewhat like non-standard take.
Right. So in logical relation, you relate terms, right? So you relate always two terms. And usually those terms need to be equal when you are not in rel. When you are in rel, those two terms, the interpretation is like those two things can be different, but they need to be at a distance d, right? So this is kind of the mental interpretation.
Okay.
Right?
Yeah.
So you see it as a pair, even though there is no pair, but yeah, semantically it's like having a pair.
Okay. Yeah, I just thought that was interesting because I hadn't seen that done before. So thank you. That was a really cool talk.
Yeah, thanks.
Hi, nice presentation. I was wondering about divergence. How do you deal with that? And what guarantees do you have?
Right. Yeah, so I didn't mention that. This is all, these are all guarantees for terminating programs, right? So usually people, what it does is like, okay, if I diverge, distance is infinite, so the definition holds. But we don't like that approach, so we say, because it's like cheating a little bit, in my opinion. But what we do instead, we say like, all the guarantees are for terminating programs. And the DSL, yeah, you need to be sure that, because it's an embedded DSL, that you don't use any pure functions in Haskell that loop forever, right? So you need to be aware of that. Yeah.
Thank you.
Okay, because we're a bit over time, so let's thank the speaker again.
Thanks. Oh no, isn't
Okay, our last speaker is Marcus from New York University. He's going to talk about TACIS, higher order subroutine logic with credits for expected costs.
All right, great. Thank you for that introduction. So yes, I'm Marcus, and I'm going to be telling you about TACIS, which is our program logic for expected cost bounds on higher order probabilistic programs. This is a joint work between all of the people up here, and my collaborator Simon is also at SPLASH'. Okay, so as we've seen a couple times now, one thing we care about when analyzing probabilistic programs is their expected runtime. So let's focus on an example here. I've got this program coin toss, which is going to repeatedly flip a coin and terminate the first time that it lands on heads. So I've augmented this program with this special tick1 instruction, which, as was again described before, is a no-op, but allows us to ask the question, how many times do we expect this tick1 function to be called? Okay, so this is not a trick question, and this analysis is pretty standard. We can let t be a random variable, describing how many times we've executed tick, and then we can basically just look at the program by inspection here and cook up a recurrence relation for the expected value of t. Okay, and so again, in this case, this is not a very tricky recurrence relation. You can see that the expected number of calls to tick here is 2. All right, so a natural question here, which hopefully I'm leading you to, is, well, how can we verify these kind of recurrence relations in cases where you can't just inspect the program and see that they hold? So some recurrence relations may depend on more complicated functional correctness properties, and we want to verify those as well. Okay, so one approach which has been fairly fruitful in the deterministic setting is this work on time credits. So this was initially pioneered by someone named Bob Atke. And the whole conceit here is that you equip an existing separation logic with this special time credit resource, $x. So the approach here says that the logic will require, every time the program takes a step, that the prover give up 1 time credit. And so overall, this means that if you can close a proof of a specification that has a total budget of X time credits, you also know that you have a runtime bound of X steps in the execution of your program. Okay, so in the deterministic world, this is a pretty nice way to structure these kind of logics. It gives you a lot of really expressive local reasoning principles. So the fact that runtime upper bounds compose additively means that they have a very close relation to separating conjunction of resources, which is good for giving credits to different parts of your proof. It also means that time credits give you the frame rule applies to time credits, and so you can specify, for example, that tick1 takes 1 time credit, and you don't need to worry about any other time credits that might be kind of floating around the ambient state of your program. The frame rule allows you to basically ignore everything else that could be happening and just focus on the cost of the statement you're currently executing. Okay, so Atke pushes his work pretty far in his initial paper, deriving some rules for amortized reasoning from these time credit rules. And there's also a wealth of research going down this road for the deterministic case. I've listed 2 of them here, but there really are many more. Okay, so then going back to our initial question, can we use these time credits to prove expected cost bounds in a randomized setting? Okay, so let's try it. Here's the coin toss example we've already kind of verified on paper so far. And I'll just unroll the computation tree to give us a little bit more to look at. So what we would want to say is that a budget of 2 credits is enough to execute this program in some sense. And let's just try to verify this with the regular time credit rules. Okay, so first we have to execute tick 1, and this costs 1 credit. And then the program is going to flip a coin and branch on the result. Okay, and the rules for time credits say that because we have 1 credit before the branch, we need to verify both branches with a budget of 1 time credit. And now things are kind of starting to go off the rails here. When we flip true, we have 1 time credit, but we don't actually need it because the program terminates immediately. And in the other case, when we flip false, we don't have enough credits to verify the recursive case here. Okay, and so you can see that no matter how many credits we start with, we are eventually going to exhaust them all with a sufficiently bad execution. Okay, so what's the fundamental issue here? At its core, the problem is that time credits give you a good way to reason about the upper bound of the maximum cost across all program traces. But in a probabilistic setting, each statement also has a likelihood that it's executed. And so this impacts the expected cost of executing that statement. Okay, so what we want to do is regain the ability to reason about these likelihoods in a way that doesn't lose us the great local reasoning features that you get from cost credits. Okay, so how do we fix this? Well, in TACIS, we have a new formulation of cost credits, which lets you prove a rule like the one I've listed here. This rule says that you're allowed to double the credit that you have in the case where you sample false at the expense of losing all the credit in the case that you sample true. And so intuitively, this is okay because we have a budget of 1 credit, and the expected budget here is still 1. It's fair coined. Okay, so let's apply this rule. You see that now in the branch where we immediately terminate, we have 0 credits, and that's fine. And in the branch where we don't terminate, we have 2 credits again, which is enough to verify this recursive call. So we can, recursively apply this procedure on and on and on, and we get this closed proof that says 2 time credits is enough to verify the coin toss program. Okay, so with this example under our belts, here's a summary of our contributions. So in our logic, we use this new version of cost credits that can prove these kind of expectation-preserving cost rules. That's our jargon for it. We also have an adequacy theorem, which is in many ways very similar to the ones presented in these other logics, including the one by Adke, which instead of giving you an upper bound on the total cost of your program, gives you an upper bound on the expected cost. TACIS also lets you define your own cost model, so your own definition for what it means to cost, or what the cost is of taking any step. And this is nice because the languages we support also have a wide variety of features. So in particular, we support higher order, stateful, recursive programs. And this is a generalization of the deterministic work that you might see in logics like the Iris $. And of course, all of this too is formalized in Iris. Okay, so before I go on to some examples, I want to briefly show you the full version of the expected cost rule. So I've written it up top here. But just, I'll walk through it informally. So let's say we're trying to verify a cost budget of X for a program that's about to take a random step. So it sort of clearly suffices to show that for every outcome of the random step, in this case 0, 1, or 2, it's enough to verify each case with an expected, or with a cost budget of X minus whatever the cost of taking that step was. So this is like the worst case reasoning that you've seen in other more classic logics in the deterministic case. But of course, our cost credits also give you a bit more flexibility. So if you're trying to prove an expected cost bound of X, we say that the prover can verify any bound for the 3 outcomes. And as long as the expected bound is within their initial budget X, regardless of whether or not the branches increase or decrease, you still can close this proof and say that the expected cost is bounded by X. Okay, so I just want to emphasize the fact that this is a local reasoning principle. If you have X cost credits kind of in your hand, and you're taking a random step, you're able to condition the value of your cost credit, and you don't need to worry about what your other credits might be doing. They could be stuck in some invariant somewhere or be in some proposition you don't care about. You really only need to care about the invariance that you have in your proof state right in front of you. All right. So for the rest of the talk, I'm going to go through 3 different examples of things that we can verify in TACIS. Here's the one which I think by law you have to include in a presentation about expected costs. So here's quicksort. So you'll notice that our implementation of quicksort is higher order. It takes in a comparison function as an argument. And so our specification for quicksort is also higher order. It takes in a specification which says our comparison function has an expected cost of m. So what we want to do is we want to verify that we have some overall expected bound on the quicksort program, which hopefully is going to be n log n, as you'd expect. And so the way that you would do this on paper is you would write down a recurrence relation which looks something like this, where you have some linear term associated to the cost of doing the partition function, and you've got 2 recursive terms where the argument depends on the sizes of the left and right sublists after you partition the list. Okay, so of course our program is not directly picking the sizes of left and right sublists. Our program picks a random element, and so the challenge in verifying quicksort is getting a correspondence between picking an index and the recurrence relation here, which is written in terms of the rank of that index. Okay, so how do we verify this in TACIS? Sort of unsurprisingly, we're going to use that expected cost rule, like I've mentioned a couple times before. So given any unordered input list L, it's not too tricky to define a function which relates the index we sample to the sizes of the left and right sublists. And it's also not too tricky to prove that if you're picking this index at random, this function here is going to be mean preserving, so we can use it in our expected cost rule. But concretely, this says that if we start with T of n credits, using our rule, we will have enough credits for both recursive calls, and we can close this proof and verify this expected cost bound. So I just want to note that this is a non-trivial problem because it relies on the correctness of partition with respect to the comparison function. And also the fact that nowhere in this process did we have to compute any closed form for this recurrence relation. Really, this separates the concerns of verifying your program meets a recurrence relation and proving asymptotic bound or something like that. We did mechanize this as well, but that was just for fun. Okay, so totally changing gears here. Let's say that for some reason we want to sample a bunch of coin flips and we only have access to random byte sampling. So for example, you might be getting your random bytes from dev random or something like that. You can sample coin flips in sort of a naive way by taking a random byte and just reading the last bit. And this works, but it's very inefficient. And so one thing that you might ask is, can you do better, right? And can you prove that you can do better? Okay, so in TACIS, I mentioned this idea of cost models before. One thing that we can do is we can define an entropy cost model. We can say that we're going to prove specifications where the time credits are used to make random samples here. And so sampling a random byte is going to cost 8 bits of entropy. So in TACIS, we can say for this section, that will mean it costs 8 credits. And so this naive approach here samples has a cost of 8 bits for every coin flip. And so, so we want to do better than this program here. Okay, so one way to do this is instead of wasting your entire byte when you sample a coin flip, you're going to cache the value of that byte in memory, and you're going to use it for multiple calls to this function. So here the program batch flip allocates a memory cell, which can store a random byte, and it allocates a counter as well. And batch flip returns a function where every time we call it, it's going to kind of pick off the next bit that we've sampled so far and return it as the result of our coin flip. So of course, after we do this 8 times, we're going to run out of these cached bits. And when we call batch flip again, it's going to need to refresh the byte stored in memory, and then it can continue onwards as you'd expect. Okay, so can we prove that this program is more entropy efficient? We can. So in our cost model that we have before, we can prove this specification for batch flip. It says that if you have 8 bits of entropy, or if you have a cost of 8 bits of entropy to set up the initial state in memory, batch flip will return 3 things, really. It returns a function, an invariant, and a specification for that function. The invariant keeps track of some amount of cost credits and also the current state of memory. And the specification says that it only costs 1 credit in order to sample a coin flip and update this invariant. Okay, so in particular, every 8 calls, this invariant will accumulate enough credits in order to do that refresh in memory. And so this is an example where we're able to derive these kind of amortized reasoning principles from the rules for credits inside TACUS. I'll also just note that this is a pretty clear example here where we're using a higher order stateful specification and higher order functions and all of the adjectives you see in front of Iris papers. Okay, final example, because I think I am running out of time. I want to show you this program, K-way merge. So let's say you have K lists and you want to merge them together into one big, or K sorted lists, sorry, and you want to merge them together into one big list. Okay, so one common way to do this is you make a min heap out of the smallest element in every list, and iteratively you pop elements from the min heap, pull them back in from the list you took it from, and so on and so on. Eventually, you get a sorted list. Okay, so what's the runtime of this program? Well, if we're able to insert and remove from our min heap in O of log k time, and there are n total elements, then we do this n times, we get a total bound of O of n log k. Okay, so half of you might be thinking, where's the randomness in this program? This is totally deterministic. Maybe you're in the wrong session. And the other half are probably thinking, can you really get these bounds without failing an undergraduate algorithms exam? So you can. There's an implementation, a randomized implementation of heaps called meldable heap, which does get O of n log k inserts and removes in expectation. And that means that when we do this deterministic looking proof in TACUS, the randomness reasoning can be totally encapsulated. Okay, and this is sort of just a nice feature of working with these time credits, which can also support the kind of reasoning that you would do in more typical cost-aware logics like the one I talked about with ATKI. So we do this in our paper. We provide a cost-aware specification for an abstract heap. We prove that meldable heaps meet this specification, and also we prove the K-way merge against this abstract notion of a cost-aware heap. Okay, so I think that's all I wanted to talk about, but thank you for your attention, and I'm super happy to take any questions.
I have a quick question.
Sure.
So have you done any evaluation with your logic?
So we've done quite a few examples, which we've listed in our paper. But unlike some of the talks we saw before, like we're not automated. This is all by hand. So
I
yeah.
see. Do you think it's possible to have something like a similar execution engine for the logic?
I mean, maybe. We've thought about automating parts of the logic, but I mean, we're sort of targeting expressivity in these sort of logics. I mean, it's coming up with these expectation preserving functions is a difficult problem, and it would be hard to automate, I think. Yeah.
Thank you.
But on the other hand, for algorithms which have a pen and paper analysis, I think that a lot of times they have like recurrence relations, which can be translated into these, something we can verify. So different approach.
Thank you very much. So let's thank the speaker again. So this is the end of the session. And it's time for lunch.
Okay, welcome everyone to Types and Gradual Typing Part 2. And we'll start with the first fun talk by Yichen Xu on degrees of separation. You just lost your... Oh, no, it's back. Okay.
Okay.
Go, take it away.
Okay, thank you for the introduction. Hi, so today we are going to talk about data races and how to prevent them. I'm Yichen from EPFL, and today it's my pleasure to present our work here. It's a joint work with my EX office mate Alexander and my advisor Martin. So first, let's talk about data races, and they are horrible. Now let's see a real story in a real-world production compiler that puzzled the developer teams for months. So this is a story shared by my advisor Martin. It's in the earliest stage of developing Scala 3 compiler. And what happened here is the parallel testing of the compiler randomly errors and clashes in 10 to 50% of the cases. And the numbers are going up. So it's parallel testing and it's random errors and clashes that really sound like a data race, right? But where it is, it's really a huge database. It's a compiler. So it took months for the team to solve it. And in the end, Martin wrote a static analyzer that rejects all global mutable states unless explicitly marked. So that's how we solved it. And where is it? It's actually a global object that contains a mutable state or mutable states. It's a seemingly innocent object for translating JVM flags. And how can I know that? It's really a huge surprise to the team. And so needless to say, data races are bad, and often they are really difficult to find and fix, so we want to prevent them. But how? There have been a lot of attempts, and essentially, data races, they are caused by concurrent access to mutable data, and where multiple threads access the same piece of data, and some of them are mutating it. So there are some type systems that try to detect and prevent data race conditions at compile time with a technique called alias controlling. That is, we use the type system to track the aliases or references to mutable data, and then we restrict them to eliminate data races at the compile time. And of them, one of the most prominent one would be Rust, which is with its ownership system. And what we are going to do here, so as we will see shortly, system like Safe Rust, it will clash with existing programming patterns, and therefore it's quite difficult to migrate existing code or languages to a system like Safe Rust. And what we are going to do is to propose a type system for safe concurrency that is flexible enough to be compatible with established programming patterns that rely on aliases. So let's first talk about how Rust prevents data races. So this example contains a data race without needless to say, and here the main function spawns a thread that mutates a vector, and then the main thread will read the length of the vector. And the Rust will reject it, complaining that there is a borrow of moved value. And this is because the threads in Rust request the ownership of the data it captures, and then the ownership system will effectively preclude all other aliases to those pieces of data. And so far, so good. And where is the problem then? So the thing is that the global alias prevention principle of Rust will obstruct with existing programming patterns. So Rust is well known to need a brand new mindset for writing Rust program. And the classical examples are secret data structures and arbitrary aliasing patterns. So let's see a concrete example where Rust clashes with some programming patterns that use alias. So first, we have a 2D vector, and then we have a function that updates either dimension of vector based on some condition. And the main function attempts to increment either dimension of a vector and at the same time store the old value. And there's no data race at all. But of course, Rust will not accept it, so it will complain there are two mutable borrows to the same piece of data. So we are not trying to criticizing Rust for its ownership principles, of course, because the benefits of the ownership system extend far beyond just data race prevention, like it enables some compiler optimizations and enables safe and efficient memory management. But indeed, the clash with existing programming patterns make it difficult to introduce these mechanisms into existing languages and existing code bases. So, and on the other hand, those existing code bases and the languages, they will benefit a lot from just safe concurrency, even without those other things guaranteed by Rust. So there's something to be done here. And what can we do? So now let's present our system. So first, let's see an example in our system. So this is the Scala equivalent of the effective example, and it relies on multiple aliases, but it's data race free. So our system is flexible enough to accept it. And now, let's say someone wants to do a parallel update on both fields of vec2 at the same time. And in the main function, given some vec2, we want to increment both dimensions of it and at the same time calculate the summation of old values. And there is indeed a data race in this program. So then in our system, the par update function will not type check. So the system will complain that we cannot show separation between PF and PG. But par update function makes perfect sense, and we can actually make it type check by adding some separation annotations. And here, these two sets are called separation degrees. Separation degrees, they signify what a variable should be separated from. And intuitively, for example, the separation degree of G means that G should be separated from both P and F. So using PF and G in parallel will not induce any data race. And if we do that, if we add this annotation, the type error will move to the application side of par update. So here we complain that we cannot establish the separation between sum and sum itself. And this makes perfect sense because it's indeed where the data races. And now let's take a closer look at our system. So our system is a lean approach to safe concurrency. So let's first explain the most essential philosophy underlying it. It consists of two parts or two steps. The first step is tracking. In this step, aliases are tracked by the type system, but there is no alias controlling or prevention by default. So you are allowed to write your code the old way. You can make use of aliases, and the code will be accepted. It's just that our system will do our best to track these aliases. And then it's only when the data races become a concern, so it's the second step, our system will look at these tracked aliases and let alias prevention mechanisms come into play so that we can obtain a static safe concurrency guarantee. So now we can focus on the first part. So the first part of our approach relies on capturing types to track aliases in types. The capturing types, they are a recently proposed approach by our group for effect and resource checking, and it has become an experimental feature of Scala 3, and our calculus is based on the calculus of capture types. So capturing types, as its name suggests, it tracks captures in types, and the capturing type takes the following form. Here, S is the shape type, like a function, a file handle, a database connection, or a mutable reference. And the C is a capture set, so it is a set of variables that the values of this type can at most capture. So for instance, the function from the previous example, this function takes an integer, adds it to a mutable state, and returns the incremented integer. It has this capturing type. And the shape type part tells us that it is a function from int to int. And the capture set part tells us that it at most captures some variable. And the type speaks out the fact that this function can refer or reference the mutable state sum. So now let's see a concrete example to see how capturing types track aliases in action. So we have a mutable variable x and its pose, which checks whether its value is positive, and have inc, which increments that mutable variable, and a check, which checks whether the variable is positive and gets disappointed if not so. And finally, we want to parallelize inc and check, which clearly involves the data race. So what are the capturing types? X has this type, so the hat marks something reference, something that we have to track the reference to. So for in this case, we want to track references to X, and both expose and inc reference X, so their capturing types speak about it, and check uses expose, so we can also see that in its type. So capturing types, to conclude, tracks all these aliasing and referencing relations in the types, and intuitively it's like forming a reference diagram or reference graph in the type system. And now that we have gathered these aliasing information in the type system, we are ready for the second part, which is use this piece of information to control aliases when data races become a concern. So now let's just consider a simplest example. Let's say we have some primitive parallel operator which runs two computations in parallel. And here the double RLT means a computation that returns a value of type T. And how to make this operator safe? So in other words, we want the type system to statically guarantee that the parallelized operations do not have data races. In our system, what we can do is to add some separation degree annotation to the parameter. So here we say that the separation degree of G is F. It means that G should be separated from F in the sense that using them in parallel does not lead to any data race. And this is a guarantee that will be ensured by the type system. And how is it ensured? We have something called separation checking, which ensures these guarantees when applying functions. For instance, let's inspect the example of this par application in the previous slide. Note that the par is dependent, so the type, the separation degree of the parameter G depends on the parameter F. And after type checking this subterm, the type is this one. So the function has a separating degree of inc. So it's expecting arguments that is separated from inc. And here, then when we apply type check this application, we will perform a separation checking to establish the separation between the argument, which is check, and the expected separation degree, which is inc here. And this separation notation is denoted this way. This separation relation is denoted this way in our system. So how does separation checking work? So intuitively, it is like working the reference graph of the two sides and to determine whether there are like shared mutations. So let's take the previous separation check as an example. To find out whether separation between check and inc can be established, we first see the capturing type of check, which has a reference to expose. And then we can see that expose refers to X in its capturing type. And then for the other side, we can find that inc refers to X as well. So there's a conflict. We will reject this check, and therefore type error will be issued for this application. So now let's talk about how our approach achieves better compatibility. So the first thing is good defaults. Although we add a new concept, separating degree, we have a default which is empty for it. So in the previous example, it's actually like this. Because we didn't specify the separating degree of f, it will be empty. And the second point is and the second point is opt-in controlling. When the parameter of a function has an empty separating degree, the separating checking will be trivial. So it's like no separating checking whatsoever. And because the implication of this is that the old code without additional annotations will just compile. And because by default, the separating degrees, they are empty, and separating checking will just be trivial in these cases. And one may always add more annotations for better, safe concurrency guarantees. And I'd like to briefly mention the reader capabilities in the system. So this denotes read-only access to a mutable state. Given a mutable state X, we can derive a reader capability Rx from it. And with this type reads a read-only reference to X, and the read-only concurrent access would be safe. For instance, this code is free from data races and is also accepted by our system. Now, let me wrap up. So there are still other interesting things I can't talk about due to the time limit. So first, our approach has been formalized as a calculus, and with parallel semantics with some interleaving of evaluation, we prove the confluence of evaluation. So we formally prove the data race freedom claim, and then the classic type soundness is also proven. And we also have prototype implementations, also check our paper if we want to see more. And so here are the takeaways. We presented our work, a flexible type system for data race prevention, and we track aliases by default, but only control them as one needs. So it's opt-in by its nature, so it's quite compatible with the existing coding patterns. And thank you very much for listening. Here is my personal website.
Thank you. Does anybody have any?
Sorry, it's getting traditional, isn't it? Thanks again for an interesting talk and a really interesting system. My main question is, in your capturing types, like you showed the curly bracket X, how does that work when the captured reference is moved to a broader scope where X is no longer visible?
In that case, we will consider X being out of scope, and it will be widened to something called cap, which is a universal capability. And the universal capability basically means anything, so it's like a top type for
right, but presumably you then lose all resolution on being able to distinguish things.
Yes, and it will clash with everything.
Right, okay.
Separation checking.
Fine. That's actually the best explanation I've heard of that about the capturing type stuff forever.
Thank you.
The other thing was, you said you don't have to annotate things?
Yeah.
But if you don't annotate things, do you then lose the data race guarantees?
Yes, so by default, if the idea is that if you are given a code base that exists and doesn't use any of the safe concurrency constructs, it will just compile, it will not break, you don't have to rewrite it, and what you do is you slowly adding those annotations to the code base to achieve more and more guarantees.
Right, but does the system have to be fully annotated in order to actually get your data race freedom guarantee?
Fully annotated, it depends. So for instance, if some place you do need some annotations to make things work, it will not compile, like you are lacking some separation degrees.
Right, but if it's not annotated, it will run, but it will be racy.
Yes, so I'm not trying to be a quick yeah.
Thank you again.
Thank you.
Right.
I was wondering about what kind of guarantees does your type soundness property satisfy?
There's three things. It's the first two is classical, like preservation and progress, and the other is confluence. So the operational semantics has some interleaving evaluation orders for those parallel constructs. Yeah.
But it doesn't tell you anything about data races? Like, you don't have guarantees about the original problem?
Well, it depends how you understand it. Like, so the confluence shows that whatever order your evaluation is, the result is always the same. So it's like implies data race freedom. Yeah. Okay.
So yeah, while you switch over, I guess following up on James's question. So when do you actually so you start with unannotated code, right? And that all works. And then you add some annotations. What's basically the threshold that you have to go over to get any sort of soundness guarantees from those annotations? Like, as soon as you add one, is it that now your compilation might fail because you didn't add enough?
Yeah.
Okay.
So it's like, for instance, if you have used some parallel operators and previously it's unchecked, and then you add some annotations, and now it becomes checked, and there might be a bunch of type errors which shows possible data races, and you have to go through them to see
Thank you. Next up, we have Litao Zhou talking about full ISO recursive types.
Thank you for the introduction. This talk is about full ISO recursive types. My name is Litao Zhou, and this is joint work with Qianyou Wan and Bruno Oliveira from the University of Hong Kong. So to give you a background, let's start with recursive types. So recursive types are useful for defining recursive data structures or expressing recursive objects. So like here is a data type list, which is recursive defined in a way that you have this list in the const constructor. So you can encode it using recursive types, where this recursive occurrence of list is represented as a recursive variable alpha, bounded by this recursive binder mu. And you can do unfoldings for recursive types by substituting the recursive variable with the whole recursive type. Like you can do one-time unfolding, two-time unfolding, and so on. And depending on the way you treat your unfoldings in your type system, there have been two ways to approach recursive types, ISO recursive types and ECI recursive types. So ISO recursive types treat recursive types and their unfoldings as equal, not as equal, but isomorphic. So for example, you have this in-L unit that can be typed, directly typed as the unfolded type. But in order to get its recursive type, you need to insert a fold operator before the term in order to do the transformation in the ISO system. So this can be described by this typing rule, where you have this fold constructors in your term language that does the folding. And on the other hand, ECI recursive types do not have this unfold and folds. So you can type a term that any types that are equal up to infinite unfoldings. So they have this special type equality relation that allows you to equate between recursive types and their unrollings. And usually this rule is defined co-inductively. So in addition to relating them between unfolded types and types, you can also equate it. You can also type this term without annotations to a different shaped recursive type, but are equivalent to the list recursive type up to infinite unfoldings. So as we see, ISO recursive types are, with this explicit term level unroll and roll annotations, you get a simpler meta theory usually, and it is also so that easier to work with when you want to extend it to other features, but that's not the case for ECI recursive types. And but ECI recursive types gives you convenience in programming. So with all these pros and cons, a natural question is, what is the relationship between these two formulations? And back in the 90s, Abadi and Fiora, they managed to show that these two formulations are equally expressive in terms of typing. So one term that is well typed in one system, you can translate it to the other that has the same typing. So the easy direction is from ISO to ECI, where you just erase the fold and unfold annotations. But for the other direction, they show that inserting fold and fold are not enough. You need to have explicit coercion functions. I will detail this in a few slides. But they show that, but they managed to show that for all the ECI recursive type equalities, you can always find an ISO recursive term, which is a function that can be considered as a coercion that achieves this transformation. So by inserting these coercions into the ECI term, you get a well-typed ISO term. But they did not consider an operational semantics in their work, so there is no formal guaranteeing that this translation preserves the behavior, such as termination of the terms in the translation. And more recently, Patrignani and other people, they show one semantic result that from ISO to ECI, this erasure translation is semantic preserving, behavior preserving. Actually, they show that it's a stronger result, that they are fully abstract, that preserves the contextual equivalence between terms, but they did not consider the other direction. So regarding this question, our paper tries to address this problem from a different perspective. So we propose full ISO recursive types as a generalization of ISO recursive types that subsume the typing and behavior of ISO recursive types. And we prove that our formulation, new formulation, is sound and complete to the equirecursive type system in terms of both typing and behavior. And so before we introduce the details of full isorecursive types, let's first take a look at why encoding equirecursive types in isorecursive types is complex. So let's consider a term t, which originally can be typed as a two-arity function, int to a recursive type. So this part of the recursive type can be folded, partially folded to the recursive type. So you can get this typing in the Eki type system. And in order to encode this typing in the ISO system, you have to insert a coercion function, which basically inserts a fold operator on the application of result of applying this t to a integer argument, which has the integer type. So after this fold, you can get the type. And this encoding loses an important property, which we call round tripping, which basically says by erasing this unfolds and folds from your encoding, it does not necessarily give you back the original Eki term. So with this example, you need to reason that this function application has the same behavior as the original term, although it is clear here that they're equal to beta and eta expansion, but you can imagine with larger programs, this semantic reasoning can be quite complex. And our observation into this problem is that it's a result from the limitation of standard ISO recursive type formulation, that it only allows you to do unfolding and folding on terms that have a recursive type. So basically, you can only transform on terms that are of recursive type, and you cannot insert this unfold fold anywhere in a term, to achieve this partial folding. So our solution is also simple. We generalize the fold and unfold operator in the ISO type system to a cast operator that not only allows you to do fold and unfolds, but also you can do more complex, deeper nested transformations. For example, you have this cast of functions that allows you to do deep transformation on a function type. And so with this, our previous encoding problem in the full ISO type system, all you need is a cast operator. So its input argument is an identity cast that keep the integer as it is, and it transforms the output type, to fold it to a recursive type. And you can see that erasing these cast operators gives you back the same original term in the Eki system. So later you will see it will help with our semantic preservation reasoning. And so in order to type these cast expressions we define a set of typecasting rules, which is standard just by structural induction on the cast operator. So it just basically describes what a typecast operator can transform between two types. And from this, you can see that isorecursive unfold and folds, the typing rules are just syntactic sugar in our, you can use these atomic cast operators to encode them that achieve the same effect of typing. And in the paper, we have more cast operator to handle more complicated mechanisms in equirecursive type equalities like co-inductive reasoning. But the takeaway is that our type casting rule is sound and complete to the equirecursive type equality rule. And with that, we can define a type-directed elaboration rule, which just generalizes the equirecursive typing rule with the full ISO term and we replace the equirecursive type equality with this new typecasting rule that generates a cast to describe this explicit cast to describe the type transformation, and we can generate correct full ISO terms that can preserve the typing. And with the help of this elaboration rule, we can state the soundness and completeness of our full ISO typing with the equirecursive typing, which says that for all equirecursive well-typed terms, you can always find a encoding in the full ISO system that achieves the same typing. So that's it about typing. And then let's talk about semantics. So we have this new cast expression, so we need to define new semantic rules for them. And we extend the values to include two kinds of cast. One is the fold cast. This is the same treatment as iso-recursive type system that treat fold expressions as values. And we also define cast of functions to be values, because basically you cannot further reduce them without applying a function to another argument. And our rules are small step call by value. So for cast expressions, the inner expressions are first reduced and identical casts are eliminated. And just the same as the ISO type system, you can cancel pairs of unfold and folds to get the value if you have this in your computation. And the more interesting rule is the push rule for functions. So in our new system, since we have this function cast as values, the canonical form of a function type can not only be a lambda, but also be this new function cast. And we need to define semantic rules to ensure their progress when it's applied to an argument. So here's our design, which is, we call it push rules because it is inspired by similar designs in the GHC compiler core language, system FC. Basically it decomposes this function cast into smaller casts and apply the input cast to the incoming argument, v2, and apply the output cast to the result after application. And in order to ensure preservation, we have this special operator that reverses the direction of fold and unfold just to ensure preservation. So if you recall our previous example, the encoding, if you apply it to an argument integer, then based on this rule, the identical cast will be applied to the incoming argument, and you reduce it to 1, and based on the result of t applied to 1, you can do further reductions, and you can see that it is preserves the typing, so this can give you a sense of progress and preservation in our system. So that's about it. That's it about type safety. And then let's see how our full ISO system has the same behavior as the ECI system. So the direction from full ISO to ECI is also simple. We erase the cast operators. And since our rules are designed in a way that are computationally irrelevant, so you can just safely erase them. So if you start with a trace in the full ISO system, if you erase all the cast operators, that also holds in the ECI type system semantics. And this theorem actually has an implication that our cast cause no runtime overhead. So you basically, in practice, you don't have to worry that the cast operators can get too large, because if you really want to evaluate our cast expressions efficiently, you can just erase them and adopt the ECI recursive semantics. And the other direction is actually also simple by induction. So the key observation is that we have this type-directed elaboration rule, so you can do encoding on it, and we can prove that for all the ECI terms and the full ISO terms related by this elaboration relation, both of them have the same termination behavior. To summarize, this paper, we propose full ISO recursive types as a new formulation that generalize the ISO recursive type system with cast operators, and we extend their semantics with the push rules, and we prove type soundness of the system. And with that, ISO recursive types are just syntactic sugar in a full ISO type system. And by defining a type-directed elaboration rule that generate erasable casts, we show that our type system is equivalent to the ECI recursive types in terms of both typing and behavior. And all our results are mechanized in Cog. And in the paper, you can find another system that employs recursive subtyping, which is simple to extend. And as a remark for future work, we believe full ISO recursive types can be useful as an intermediate language if you want to compile a source language using ECI recursive types, because this explicit cast gives you information about type unrolling and rolling, so it will be beneficial for an internal analysis or optimization. And since our casts are runtime erasable, so you can erase them in your target language of the compiler to get efficient performance. And on the other hand, we also think we are also considering full ISO recursive type as a useful language design on its own, and we plan to extend it with other advanced type system features such as intersection types, polymorphism, to give us interesting programming encodings. So that's all for my talk, and thank you for your attention.
Cool. Do we have any questions? Okay, I'll start with one. So does that mean now that you kind of, because before if you wanted equirecursive types, you had to kind of go in co-inductive land, and that's not as pleasant as, you know, just staying with inductive types, that you can actually do that, and that you just, you know, have your equirecursive types in your language and then automatically translate to fully isorecursive, or are you in co-inductive land there too?
So actually, what I'm hiding from in this presentation is we have some more cast operators. Like you can do fixed points on a cast operator that can describe those co-inductive cyclic reasoning in equirecursive types. So we are able to encode that. Actually, in the literature, you can find those papers that describe how to find this derivation. So you can essentially in our paper, you can also derive this cast automatically based on these co-inductive rules. Yeah.
Any other questions? Oh, in that case, let's thank Litau.
Thank you.
Have a quick break until we
Yeah. Definitely not confusing ever.
Okay, and we're back with talk number 3. Oleg Giecek with gradually typed languages should be vigilant.
Thank you very much. So today I'll be presenting our new gradual typing correctness property, which we call vigilance. So to start, in gradual typed languages, you have fine-grained interop between typed and untyped code. So how that comes about oftentimes is you have an untyped language that decides, okay, we want to adopt typing. We want to let users add type annotation to their program. So like in this example, we have both an argument and a result annotation on this function. However, there becomes a problem, which is that as soon as the language designers do this, well, they have a whole standard library that's untyped. And now they're kind of forced so that if users really want to use types throughout their program, they're going to have to somehow quickly give them access to these libraries while also having types. So a common solution here is that you make this typed interface. So here, this untyped user is calling a function, a segment PNG function from a typed library, but they don't necessarily know. But the library designers decided we're going to add types to this later, and instead just call a untyped segment function. And then that value flows back to the untyped user, and the untyped user expects this to do exactly what the type tells them, which is return some kind of pair of PNG. Now the problem is, what if this untyped library is buggy and sometimes doesn't return PNGs, but maybe returns, JPEGs in some cases? So the question is, what does the user actually see now? And the answer is, it depends on the cast enforcement strategy. So in one case, in the natural semantics implemented in typed racket, they actually see the PNG cross PNG no matter what. And the way that natural does this is they have higher order contracts that wrap functions, and they perform so-called deep checks, ensuring every single type is accurate. There's another semantics called transient, implemented in a system called reticulated Python, and they just check the top level type constructor, just shallow checks, but they make sure they check enough so that they can ensure safety. So in that case, the user only knows that they're going to see a pair, but they know when they do more stuff with it, every interaction will be safe. And finally, there's erasure, implemented in TypeScript, and this is just the case where you have no checks, and the user sees this as documentation, but they have no dynamic guarantees that they actually will see a pair of PNGs. In general, it turns out that this corresponds directly to different type soundness theorems. So Greenman and Feleisen showed that there's actually a spectrum of type soundness theorems depending on the operational semantics. So from the same statically typed term, depending on whether you're using the natural, transient, or erasure operational semantics, you'll get either a type, a tag, top-level type constructor, or dynamic soundness theorem. And to make matters worse, it turns out that type soundness is not even enough, because they showed that there's another operational semantics that's error equivalent to transient and yet has the same kind of type soundness guarantee as natural, which is quite odd. And to make matters even worse, let's go back to our untyped user program. At the end of the day, this chopped function is untyped. Even though they're inside the function calling this typed function segment PNG, the outer function itself, if somebody else calls chopped, all they know about it from soundness is that it behaves like untyped. So if you have a semantics that forgets casts after some amount of casts back to dynamic, then the user doesn't get this guarantee anymore that they're actually going to see pairs of PNGs. So how can we go beyond this? So let's see what exactly happens as we flow values through this program. The user takes an image and sends it to segment PNG. In segment PNG, we see this PNG annotation, so this becomes kind of an assertion that the user has that the image better be a PNG. And then that gets sent into segment. Segment produces some value after running. And when it goes back to segment PNG, it sees the annotation and sees this value better be a pair of PNGs. And finally, it goes back to the untyped chop function. So over time, we see as we run a gradual program, we get these kinds of assertions like image better be PNG and V better be a pair of PNG. So now there's the question of how do we know these insertions are actually enforced? In the prior work, complete monitoring, they prove a syntactic theorem that basically says that at every one of these type assertions, there is some check that happens. However, because it's syntactic, they actually don't have a way to precisely say what those checks are. So at best, they can say that some check happens. So in particular, there can be languages that have checks that always succeed, and that can still be a complete monitor. So it's not quite the property we're looking for here. So in general, we can try to do a bit better by saying, okay, as a value flows, it accumulates type assertions. So let's collect them all. Let's give that a name. So for example, if we have some blue chunk of code and it produces a value at type tau1, then that value flows into some purple chunk. Now we know not only should it behave like tau1, but it should also behave like tau2. And as it flows into this red chunk, we accumulate an additional tau3, and into the green chunk, we get tau4, etc. So let's call this list of types a typing history. And now we have more precise language to say what we want. We want to say that a value behaves like its typing history, okay? Now the question is, what does behaves like mean? And this is kind of the key idea that formally supports our approach. We're going to use a semantic model to specify that precisely. So now we can introduce vigilance, and we'll say a type system in operational semantics is vigilant when every runtime value behaves like its typing history. Okay, so there's a couple things to tease apart here. Exactly what do we mean by behaves like a type? How do we know what typing history is associated with a runtime value? And what does it mean to behave like a typing history? So starting with behaves like a type, we're going to use a particular kind of semantic model called a type soundness logical relation. And the key idea is that we're going to have essentially two sets for every type. A value relation, so we'll say that a value is in the value relation at tau when that value behaves like tau. And then similarly for expressions, we're going to have an expression relation, which is expressions that run to a value that behaves like tau. So that calls back into the value relation. Okay. Now from here, to actually collect up those typing histories, every time a value crosses a cast, we're going to accumulate the boundary types on those casts. So if we know that V has a typing history tau bar, and we see that we cast it to tau prime from tau, we're going to add those two types, tau prime and tau, into that typing history. But how exactly do we have that association in the first place? Well, we're going to instrument our operational semantics to label every value and track values and types in what we call a value log. So we're going to use sigma for that value log, and the type is going to be mapping locations to values and optionally pairs of types. So why an option? To begin with, let's consider the case before where we have this value running from this blue component. In this case, this blue function hasn't introduced any casts. It's just a single chunk of code that runs down to value. We don't know any types yet, so we just put in none. Now this value gets sent into this purple code, and now we get an additional type tau2 from tau1, and now we annotate that new value in a new label along with these types. And similarly, as we go into the red chunk, we get a new label and a new type, and so on and so forth. Okay, so we have some instrumentation here. How do we incorporate this into the logical relation? How do we get to typing histories? So we notice something, which is that a value log is kind of like a store. And so we can use a very common technique in logical relations, which is that we'll add a store typing into our semantics, which tells us what the type is for every location. But in this case, we're actually going to associate every location with the typing history itself. So now we'll have two additional members of our logical relation. We'll have the store typing, the value log typing, and the value log itself. Okay. So that's how we get to typing histories, but we still have one more component, which is what does it mean to behave like a typing history? And to do this, we introduced this notion of a value history relation. So it's supposed to be the whole typing, basically the value relation extended to the whole typing history. And it's basically the same as just saying that the value satisfies every type, or the value behaves like every type. And finally, we can say the formal statement of vigilance, which is that a language is vigilant when for any well-typed E at type tau, then it is in the expression relation at tau with empty value log and value log typing. And we can extend this to open terms in the completely usual way. And stepping back, summarizing, we now have a bit of a recipe for vigilance, which is that if you have a type system in operational semantics and you want to show that it's vigilant, well, you're going to start with a type soundness logical relation. You're going to instrument your operational semantics with a value log. And then you're going to add the value log and value log typings to your logical relation. And finally, you're going to require every label in your value log satisfies its typing history. Okay, so now that we have vigilance, we can ask what satisfies vigilance. And it turns out there's a spectrum, just kind of like type soundness, which makes sense because we built on top of type soundness. So similarly, we have a dynamic vigilance for erasure, we have a tag vigilance for transient, and we have a type vigilance for natural. But importantly, this is enough to distinguish amnesic from transient. They don't have the same vigilance property. So looking at this, we kind of wanted to perform a design exercise, which is, can we do any better for transient? Because we were noticing something while looking at transient programs. So transient performs tag checks on casts and elimination forms. And that's key to the safety property. But it also means there's something more interesting going on than just the top level type constructor. So in this example, we're taking in a pair of PNGs and returning a PNG, and we're just taking the first projection. So because of the essentially tag soundness result, all we know about the argument coming in is that it's a pair. However, on the first projection, we do this check that actually gives us more information about what's in that pair, namely that it's now a PNG. So using this kind of idea, we can actually show that many programs with under transient have much stronger types than just the tag. So for example, in this program, it's not just a pair, it is a pair of actual nat and int, because we can just examine in the first case that the only way this can run to something that's not an error is if it's a nat. And in the second case, it's definitely an int. Doesn't matter how many checks go. So Greenman-Fleisen said, okay, transient satisfies tag, but we want something truer to the behavior of transient. So we designed this truer transient type system, and the key ideas are that on introduction forms, we remember the type information we've had, and on elimination forms, we learn type information. So in the case of remembering, if we have a pair, we actually remember, in the case where the first component's an int and the second component's a nat, we don't just say pair, we say int cross nat in the normal semantic way. And on elimination forms, we look at that, check on that projection, and actually learn additional information about the type that sits there. And so the key to this is a lattice of types. And the idea is at the top of the lattice is the least precise behavior, and at the bottom is the most. So when we say learn type information, we mean meeting in this lattice. So notably, we have a dynamic type, which is our top least precise behavior. It captures all of the behavior you could possibly have any term. And then we have the bottom, which is the most precise, which is terms that definitely err. So there's no value that satisfies the bottom type. So that is definitely going to err because of some cast. Now we also have that ints can be refined into nats. We have that pairs, unsurprisingly, are component-wise. But on functions, we have something a little weird, which is that they always have the argument star, which for people kind of used to type precision, this might be a little bit surprising. And the key idea here is we're talking about transient behavior. And when you talk about semantics, semantic subtyping is a contravariant notion, not a covariant notion. And it's really intuitive in the sense that if you have a function that takes in nats and returns nats, then you just know it can take in nats. But But if you have a function that can take in a star, you can always treat it like a nat arrow, a function that takes in nats, but it can take in ints, and it can take in bools, and it can take in functions, and whatever you want. And it'll still act safely. So that's the idea here. Any transient function is actually safe when applied to any argument, which is kind of a surprising result that we think people didn't really emphasize enough. But anyway, moving on from here. After we developed this type system, we actually noticed that you can perform a very simple operation, which is that if we don't learn anything on a check, which is kind of like saying we do a meet and it just ends up at identity, it didn't move your position in the lattice, we can just remove that check because it's effectively a no-op, right? And it turns out just this grabs almost all of the optimizations in a previous paper, which we found was quite interesting. So it turns out that just having this little bit of flow sensitivity in the type system kind of like made optimizations come for free. Okay, so back to our spectrum. We've added a new position, namely that transient is vigilant for truer types. And moving on to future work, we're looking, my next project basically is to look at gradual borrowing and see what vigilance means in that context. We also have a conjecture that abstracting gradual typing produces vigilant languages by construction, and we'd love to see if that's true. And I also have interest in thinking about optimizations from the perspective of typing histories. So in summary, vigilance describes what types are enforced at runtime using a type history. And the fact that it's semantic means that vigilance prescribes behavior, not necessarily just checks. And if you want to see the paper and more, you can check my website, elixir.pl. Thank you.
Thanks, Oleg. Do you have any questions?
Hi, thank you so much. This is awesome work. I'm curious how this idea extends to, how it would extend to situations where you can have like closures over mutable variables. So in the case where you have some variable, it goes through a bunch of casts, we accrue this typing history for it, and then it is captured by a different function. There's some mutation that happens, may or may not invalidate some of those casts, or some of the things in the typing history, right? Do you have any thoughts on like how, or I guess, does this paper address that case? And if not, do you have any general thoughts on how that could be handled?
The paper does not address that in particular. I think, so if you take the case of something like a monotonic references, then the problem is solved for free because it's by default. My conjecture is that you need some amount of indirection, some extra indirection in the typing history so that it wouldn't just be types, but like you could have some, section that might get cleared out a bit after the mutation and then build up new types as you get new assumptions.
And then I had one other question, which is with the typing history, since you kind of have this rich and flow-based log, I guess, of all the places the type has been and various assumptions that were made about it in elimination forms. Given that you have that information, if you wanted to give an error message or show blame or something for a type error, right? What kinds of interesting things could you potentially do given that you could say, oh, it violated this assumption that happened at this time, but not these others?
Yeah, so blame is something kind of that we didn't cover at all, and we do feel like there seems to be some like very strong connections we could make. My feeling is that the typing history should, like the semantic idea of why you wouldn't satisfy a typing history should basically exactly align with that error. And so if we enrich the typing histories with more source information, we kind of feel like that should give you a blame correctness theorem as well. But it's stuff we haven't explored yet. Thank you.
Thanks again, Oleg. So next up, we'll have Wenjie Ye talking about merging gradual typing.
Hello everyone. Welcome to my talk. My name is Wenjia. Now, currently, I'm a postdoc in National University of Singapore, and I'm glad to be here. Today, I will introduce the joint work merging gradual typing with my PhD supervisor, Bruno, in the University of Hong Kong, and Matthias from the University of Chile. In some calculi with intersection type, they use a special operator called a merge operator, and we use double comma. And it allows building values that can have multiple types. For example, in the program, x has both an integer and a Boolean value. And when x is used, it can act as either an integer or a Boolean. And the semantics of the merge operator is type-directed, which it means that components are extracted from merges based on types. So, like in this typing rule, one merge with true is typed as int and bool, and we can always extract a supertype from a merge. And the interaction between subtyping and the merge operator is subtle. So let's see, in this program, x has type L2 and bool, and the value for x include a field L1, which is hidden due to subtyping. Then the merge operator appears to be statically safe. However, what happens when we do the field lookup? If the original field L1 is preserved in x, then when we later look up L1, there will be two L1 fields. And if we use a bias lookup, which return either the first value from the left or the second value from the right in the merge, then the semantics of the program may reduce to a surprising behavior. For instance, in this program, string boom will try to add to an integer, which will crash the program. And noted that the type-directed extraction of values can lead to ambiguity. Consider the program. This program is ambiguous because the result can be either 1 or 2. And to address the ambiguity problem, as well as the problem arising from the interaction between merges and subtypings, which I mentioned before, so some restriction is proposed, which we only merges values that have disjoint type. So disjointness will reject ambiguous programs, such as 1 merged with 2, because these two values has the same type int. So they cannot be merged. And merges has many useful things. So they can model complex mechanisms. For example, in calculi with a merge operator, multiple field records are merges of single field records. So they can be extensible at runtime. So they can solve like expression problem. And the merge operator can encode various other programming language features, including extensible records, dynamic typing, and operator overloading. And recent research have further shown programming language design such as SDL or CP based on variant of merge operator. And this design enables some advanced OOP features such as first-class classes. And in particular, calculate a language with the merge operator can model, as I say, dynamic or object-oriented programming features such as first-class classes and dynamic inheritance, which are supported in TypeScript. For instance, in the above CP language, circle extends shape with a method to calculate the area of a circle. And the superclass shape is a function parameter, which means that circle can be extended by any shape at runtime. But however, CP is a static language, which is restrictful thing. So the question is, what happens if we don't fully know the interface of the superclass? What happens if we would like to extend any trait with this area. And we would like to do something like this, which you can do in TypeScript. But we know that in TypeScript, this behavior is unsound, so we want to be sound. And so we want to make sure to detect the ambiguity error at runtime. For instance, you may extend a trait that already have a class that already have an area function. So to address this, we can follow the gradual typing approach, which combines static checking with dynamic checking, and you can move from fully annotated program to no annotation program. So you can have here, for instance, on the left, a lambda takes a function from int to int and fully annotated. And on the right, you have the same lambda without an annotation. And now with gradual typing, you can have like partial annotated programs. So you have the lambda takes a function from anything to int. So the input can be any type. So what interests is that both gradual typing and merge operator use type-driven semantics. So this is a good opportunity to have a unified foundation for type-directed mechanisms. And we know most gradual languages are built like this. So you have the source language, which have the type checker, and then the separate runtime semantics, which is given by an iteration to a target language. And this target language has its own type checker and runtime semantics. And this is usually called cast calculus. So in this paper, we present lambda m star, where the static semantics and the runtime semantics are defined in the same language, where we don't resort to a cast calculus or like a target language. And we use a bidirectional type checker for the static semantics and the type-driven runtime semantics. Yeah, so the runtime semantics define over the source language directly. And the interesting thing is that cast and projection are mutually defined. So for instance, this is a gradual program which uses merges. And we add this star type, which is unknown, or dynamic type, and it can represent any type. So this is a function that takes merges of records of with type int and with something else. This should be type checked. Then I will introduce some key points and challenges in our work. So one of the key aspects is the disjointness, so which I have introduced before to solve the ambiguity program in merge operator. So for the formal definition of disjointness is that two types are disjoint if they have no common supertype different to top. So for instance, int and bool are disjoint. Int and int are not disjoint. And two functions are not disjoint because they have this common supertype, which is bottom to top. Then how to deal with a star? It's non-trivial. We use the extensional lifting of the disjointness. So basically, every type is disjoint with a star because a star can represent any type like top. So the other important thing to mention is that there is a notion of ambiguity error and type error. There is a distinction. So to explain this, we can look at this program. We have merged 1 with 2, and it's cast to int. So you try to cast 1 to int, you get int, and 2 to int, you get an error. But you only want to have one value returned, so you return 1 as the result. Then, if you have 2 values, you have an error because they are ambiguous. Like for example, here with gradual types, you can have multiple numbers, which can be type checked. Even we have disjointness because unknown type is disjoint with any other type, and this could lead to ambiguity error. So this is an error. So you can have this slightly more complex example, like the previous one, but now merge with 3. And if you try to do the same, like the previous one, 1 star and 2 star reduced to an error, and 3 star reduced to 3. So in this case, if we try to apply the first rule, then we return 3. But we don't want to do that, because we want to say that this should be an error, because it's ambiguous. You have 3 numbers. So instead of having an error, we have 2 kinds of error, types and ambiguous error. So we only return a value if the case is a type error. And if one of them is ambiguous error, then we propagate this error. And the other interesting thing is that we preserve modular type-based invariance. So to explain this, we can consider this. B is a subtype of A, and C is a subtype of A. And if you have a program that says let X of type A while new B in E, and you know by modular type invariant that X cannot access full, because X doesn't have full member. This is also true for merges. You can have this program which loses precision on the subtyping lattice, and you are saying X have L1 and type int. And if you bind this X to Y of type star, and then to Z of type L1 and type int, and L2 type bool, then you should not be able to project L2, because X doesn't have a bool. So it should give an error. In this case, our lambda m star reduced to a type error as our expectation. And the last important thing is gradual guarantee. The gradual guarantee is a property in the gradual language which talks about imprecision. So imprecision is a relation between gradual types, where you can say that one type is more precise if it's more static. So for instance, star is the most imprecise type. And the gradual guarantee is separated into the static gradual guarantee, which states that typing is monotone with respect to imprecision. And so if you have a program type check, then a less precise program also type check with a less precise type. And the dynamic gradual guarantee, which states that reduction is monotone with respect to imprecision. So if you have a program that reduces to some values, then the less precise program should also reduce to a less precise value. And the thing is that in lambda m star, the DGG is not satisfied. You can think of this program. You have a variable x that is an int, extract from a merged 1 with 2. Then you have variable y that is a bool, extract from a merged 2 and false. And z is extracted from both x and y. So first case, 1 is projected. Second case, false is projected. And finally, false will be projected. But if we lose precision, for instance, now we say x is star, and y is a star, and we don't know what to project. And if we try to project bool from x and y, we are going to get an ambiguity error, because we don't know what to project, true or false. So DGG is broken. But we prove the DGG is satisfied, modulo ambiguity error. So here is the original DGG, which says if a more precise 10 E1 reduced to a value, then E2 reduced to a value, and 2 values are in imprecision. And also, if E1 diverges, then E2 diverges. And there are 2 more cases. So we prove the DGG modulo ambiguity error. So in this case, if E1 reduced to a V1 and E2 reduced V2, and V1 is more precise than V2, or E2 can reduce to an ambiguity error. But here we need to use a semantic notion of precision, because for instance, one merge with true cast to int, you could get 1 if it casts to unknown. Nothing will be projected. And the other case is that if E1 diverges and then E2 diverges or reduced to an ambiguity error. So if you can think of this program here, where the first expression diverges, but the second one gives an ambiguity error because they are 2 integers. So there are more in the paper. You can have a look if you want. So we have the formalization of lambda m star, meta theory, which are proven in Koch. Main theorem are about determinism of reduction, type safety, conservative extension of the static discipline, and the static gradual guarantee. We also have the dynamic gradual guarantee proven on paper. And also we encode the static semantics of GTFL, which is the calculus from abstracting gradual typing. So in summary, our work, lambda m star, which integrate gradual typing and the merge operator, it's a direct gradual language without resulting to a cast calculus. And we support advanced OOP features such as first-class classes and the dynamic inheritance. And we distinguish 2 kinds of error, which are type error and ambiguity error. Moreover, our lambda m star satisfy modular type invariant and dynamic gradual guarantee modular ambiguity error. That's all for my presentation. Thank you for your listening.
Okay, time for questions. I guess we'll start with one. With the merge operator, right? One thing that you said in the original applications that it had was sort of overloading. But here you seem to say that that you rule out cases where basically functions seem to never actually be allowed to have multiple ones merged. So what's the difference between kind of your merge operator and like the more classical merge operator?
Actually, our we also consider to allow merges of multiple function, and at first it caused some problem for in a dynamic gradual guarantee, but we think it should be allowed in the future work. Yeah.
Okay. So how do I think you didn't really show record types, right? Do you have separate record types, or do you just model them as like single field records that are merged?
So for record types, we for multiple field record types, we are encoded by a single field records merges. So it's okay. Many single field records are merged. So they can be multiple field records.
Okay, but they have individual field names, do they?
Yeah.
Okay.
Yeah, they have individual field name.
Okay, cool.
What would be a use case for deliberately? So okay, I guess you showed these 2 types of errors. They're typing errors and ambiguity errors. In the case of a typing error, it doesn't return a value. In the case of an ambiguity error, it propagates that error, right? Sorry, you had a slide. It had 2 kinds of errors, right? There was typing and I think it was this one, yeah. And so it propagates the ambiguity error. Yeah. Yes, that one. And so I'm curious, I guess, about the decision to handle these things differently. From a programmer perspective, when would be a situation where I would want to write code that introduces an ambiguity error, or like have this intersection? So why would I, if I were writing code that said something like x is 1, 2, that would give an ambiguity error if it were subsequently used in like the code there. Yeah. And so I feel like it would be useful if the compiler would tell me this is ambiguous.
Yeah, if it's dynamic value, like if you annotate it with star, it means that you want to pass the type checker, so it will not detect at compile time, but it will be detected at runtime.
So it's just in the case of star?
Yeah.
Okay, thank you.
Thank you.
Thanks, Ed. Okay, and so.
Oh, sorry. Can I keep that? Can I give it back to you?
Thank you. So for our final talk, we'll have Anastasia Kravchuk-Kirilyuk.
Okay, one sec. Just, I'm going to. Can you see it now?
Yes.
But it's not full screen? Okay, I will make it full screen once you show it. Yeah.
Okay. Talk about nested family polymorphism with persimmon.
Thank you. Apologies about this chop job. All right. So, hi, I'm Anastasia. If you haven't met me, I'm a fifth-year PhD student at Harvard. And I will be telling you today about persimmon. So this is a joint work with University of Waterloo, and besides myself and our team, we had two wonderful undergraduates, Gary and Jonas, and of course our advisors, Professor Yizhou Zhang and Professor Nada Min. And before I dump a load of details on you, I just wanted to give you a small overview of what I'll be talking about. I'll begin with a motivating example to show you why we care about this sort of thing. Then I will dive into the discussion of the features of our language and how we support them in the calculus. Then finally, I will conclude with some takeaways. All right, so now for some details. This is the motivational example. It's going to be about extending a compiler, and compilers have a bunch of nested components inside of them. So like at the minimum, you would have a source language. For example, here it's simply tap lambda calculus, and you might have some target languages, well, you should, where here in this example, we have a target language that converts simply tap lambda calculus terms using continuation passing style, and then we have yet another target language, just for fun, that converts those terms using closure conversion. And of course, we have these translation functions that do the thing. Okay, so as you can see, even within this solitary compiler, you already have some opportunities for extension. Like these two target languages actually share some terms, so maybe you wouldn't want to have them completely separate. You might want to have them both extend some intermediate language. Here it's marked IL. All right. But let's take this one step further. Maybe we will actually like to extend our source language. So languages change over time, and we might want to add some features to our base SDLC, which is kind of weak right now, but we might want to add things like if statements to it, right? And while these tiny changes, something like adding a case in a match or adding a constructor to a type, they propagate throughout the rest of this compiler, right? Because everything depends on the source language in this compiler. And we don't really want to create an entirely new compiler for every version of SDLC that we might want to support. So instead, what we might want to have is an extensible compiler. So here I've shown you an extension ifext, which is a compiler that is an extension of basecomp. And what do I mean by extension? It inherits everything inside basecomp, including all of the nested components. It retains all of the relationships that are there between all the nested components in basecomp. And then also it adds some new code to extend our new features as we want it. All right, and I just wanted to say that what we do is, in Persimmon, is we accomplish this sort of nested extensibility using nested family polymorphism. There's a lot of work in this area. A lot of people care about extension of stuff. So I just wanted to tell you what we care about. And we care about the fact that family polymorphism is actually an extremely elegant vehicle for this kind of nested extensibility. I will show you how, you'll love it. And then some things we almost get for free. So for example, composable extensions or mutually recursive references, and we even get to avoid a lot of the parameter clutter that usually comes with extensible code. All right, now that we have set the big picture, I will tell you more about the features. I'll explain how we support extensible variant types, or they're also called algebraic data types, ADTs. I will talk about how we support extensible pattern matching that is sound for the new cases, and also, of course, nested inheritance. All right, let's start with the easiest thing. That's an extensible variant type. Because we're in a family polymorphic calculus, we're using families instead of modules. So we have a family STLC base, family STLCF that extends STLC base. So we're sticking with the previous example of adding if statements to the base STLC. And in order to do that, well, we might want to add the Boolean type to the types of the system. Here, this is persimmon code, so we get this lovely plus equal sign, which is a very small symbol that gives you an extension. Yay! However, of course, things are not as easy under the hood. What we want from this, actually, is that this type tie that's defined in the extension doesn't just have this new constructor tbool. We also want it to have all of the previous constructors that it had before in the base calculus, okay? But not only that, right? We also expect that any recursive reference to the type tie in the extension will reference the extended type tie in green and not the ugly old base type tie in orange, right? Okay, so that's what we call family polymorphism. This means that the constructs that we define are polymorphic to the family that they're nested within. Okay? You might wonder, why isn't subtyping enough? Well, first of all, this isn't subtyping, right? And a lot of people have mentioned this before, but if you want to read a cool paper, read that. And even if they were subtypes, this still doesn't solve our problem of the fact that when we model systems, we often have definitions that are dependent on each other, right? So here, for example, values and expressions reference each other recursively. And basically what I'm saying is that you might not want to let expressions from the STLCF calculus interact with values from the STLC base calculus. That's not going to be sound. You're not going to be able to even evaluate your expressions in that case, right? And now for the fun part, what we basically have is two families of types, right? Kind of like cats and dogs that we might not want to let them interact as much. Okay. So how do we support this, right? Okay, it all looks great and all, but how do we support this in our calculus? Well, we represent each family by what's called a linkage. A linkage is just a data structure. Don't be scared. It's like a map of maps. And it contains all of the typing information about a family, right? We also have linkages for the definitional information, but I'm not going to show that here. Let's just keep it easy and stick to typing information. So our STLC base calculus is going to have a linkage representation, and so will our extension, STLCF. They're both families. They both have a linkage. Okay, and so how are we going to actually combine the two to create this fully extended version of STLCF? Well, we have this wonderful operation called linkage concatenation that does it for us. And what basically we do is we want to create a complete linkage. We call it complete because it has the inherited information and the new information both in it. So of course, we'll have the new constructor tbool, but we also want the other constructors that we've inherited. And now, notice a problem. Okay, I haven't mentioned anything about these weird orange things, right? These are paths, okay? So each type is annotated implicitly with the path for which family it is in, right? So before our type tie in the linkage for STLC base, it was referring to family STLC base, right? So this orange thing is just a path to the family that the type is nested within. And prog just means program. So it says STLC base is a top-level family. And the self wrapper around it basically says it's going to adapt upon extension. So it is a type, it's a relative path type, and this relative path will adapt once the code is inherited. So here, bam, we've replaced these paths with the paths to the new extended version of STLCF, right? And this is important because this is what keeps the code sound for reuse in the derived family, right? So it's all about these paths that reference the family, and it's all about substituting these paths, okay? All right, now, pattern matching, right? Let's stick with the same example. Consider maybe a substitution function, and this is in the STLC base family, so it has two cases for the two constructors of exp that appear in this family, right? So it only has two cases for now, but then once we want to extend the calculus, we add a new constructor to expression, EF, right? And once again, with the plus equals and persimmon, we add a new case to this function, right? So we're matching on expressions here, and now that we have a new constructor that creates expressions, we want to have a case for that one too, right? So, okay, that's great, but how do we know that it's sound, yet again? All right, so under the hood, things are again uglier. The user doesn't see this, but I do. Basically this function from the base calculus, and well, from the other calculus too, but let's stick with the base for now. It's going to be separated into two parts. There's going to be kind of like a header function that has a match expression in its body, and then the match cases are actually going to be completely separate. It's going to be a separate top-level family polymorphic construct. And the use of that is that, well, this cases construct is now family polymorphic as well, so it also adapts to the family it's nested within, and when it is inherited, the paths will be updated just as I showed you before. And something else that's interesting is we're a fully static family, so we love annotations, right? So this cases construct is going to have more typing annotations that we're going to need for type checking. And this first one that I'm showing you is it's annotated with the type that it's matching on, right? So it's saying here, I'm matching on expressions, and if you remember, there's an implicit path there that points to the family where this cases construct is coming from. So once it's inherited, that path is actually going to be updated, and it's going to say, oh, actually I'm matching on expressions from this extended calculus, not the one before. Okay, so that's important. Then this one's not so important. This is just the input type. It is any extra information you might want within the pattern match. So here, it's just those extra arguments from the actual subst function. And then my favorite, the output type, in fact, exhaustively specifies every constructor that is matched here. Okay, so it is a very detailed type that says this cases construct only applies to the eval constructor of exp and the eap constructor of exp. And this output type is what's going to help us statically check existivity of the pattern match cases after extension. All right, so here I'm showing you this complete version of the cases from the extended calculus. So basically, we have this new EF case, and then we have these old eval and eap cases, and all the paths have been already substituted just for time and comfort. So how do we check that that is actually exhaustive? Well, this thing is in a linkage, right? And we have these linkages that have all of the typing information. So we're going to look up the definition for expressions in this same linkage, and because expression was extended, it already has these three constructors that we need to check for. So it's saying this type definition has three constructors. Your cases better have three constructors, right? And if it does, everything is awesome. And if it doesn't, let's say the user forgot to put in the EF thing, no, this is not good. So this will not type check, right? All right, finally, I will tell you about nested inheritance. So I basically, said that in the beginning that this is really elegant for nested inheritance. And the reason for that is because our linkage representation and this path substitution mechanism work really well together to extend deeply nested components, okay? So I'm just gonna show you a slightly more complicated example. Let's say we have a program with two families where there is family A1 and A2, and A2 extends A1. And then within A1, there are also two nested families where B2 extends B1. And now because A2 extends A1, it also gets all of those nested components, right? So there is another B2 and B1 in A2. And actually, those two nested families in A2 further bind the ones in A1. And probably add some new code. Like all of these relationships are getting very complicated. All right, so what if our goal is to type check family A2B1? It's kind of deeply nested, not so deeply that you can follow, but very, very much different from the previous example we looked at. So first thing I'm going to tell you is that we need to compute some linkages to do this type checking, but we don't start with A2, B1, okay? So we're deeply nested, we don't even know how long that path is, right? So a really much better base case is to start with prog, which is of known length 1, the path, right? Okay, so we're going to do this linkage computation from the outside in to prevent infinite loops and, you know, to have great things like a good base case for your soundness proof. We're going to say, okay, the first thing we do is we compute a complete linkage for prog, the program, which is just parsing the program, right? And another important thing here is that we don't actually recurse to the nested families automatically. So a complete linkage for a family will have incomplete linkages as nested, right? So it will not recurse, it will just parse those families and it will keep them around, but it will not make them complete to prevent infinite loops, right? So once we've done that, well, we might want to compute the linkage for A1, which is the parent of A2. You know, we're going to A2 next, so we might need to know what the parent of it has. And then, of course, we compute the linkage for A2, and then now we're ready to compute the linkage for A2B1, but one important thing that I want to point out about this computing linkage for A2 is that any further binding of A2B1 also happens here. So now we've also copied over any code that is contained in A1B1 into A2B1, okay? Just so you're not worried that we forgot about it. It does happen. And then now we can finally compute this linkage, and with this linkage we can type check this family, okay? And I hope that, you know, gets you excited about the possibilities of type checking really deeply nested families with extensions. I'm very excited. Okay, so some takeaways, right? We have extensible variant types, extensible pattern matching, nested inheritance, all of its own. We have family polymorphism, so all of this is about the constructs being polymorphic to the families they're nested within, whether it's from the beginning or after extension. And the cool thing about our match case is that they're also direct family members, which means that they are directly extensible, just like our variant types, right? And the stars of this whole mechanism are relative path substitution, which helps us adapt code for reuse. And then the linkage representation of families helps us with extending all of these very deeply nested families. And that is a website you can go to get a lot of links and things. Yeah, and with that, thank you for listening.
Hi. Thanks for the talk. This looks like a very nice language design. I'm slightly concerned about the usability because, as far as I understand, the type checking occurs on the linkage level, right? So there's a lot of, as you mentioned yourself, there's a lot of ugly stuff that lives behind the hood, right? Under the hood. And so is this going to leak to users as part of the type errors, and how do you ensure a good user experience?
Right.
Yeah.
That is a great point. So I do think currently it either type checks or it doesn't. So there's definitely room for improvement in terms of, you know, user experience. However, they do not see the theory, which is a great thing. We do have a lot of sugaring. We have a lot of comfortable features for the users, such as like the function that we have here, like this is subst is fully sugared, right? The user does not see the breakdown into the top, like the function in the cases construct. So, yeah. But
right. But what does the error message look like? You know.
It would just either type check or not.
Okay.
Yeah, you're right. Yeah.
Okay. Cool. So that's future work for improvement, right?
Potentially, yes.
Thanks for the talk. I was interested in whether your type checking is modular.
Oh, that's such a great question. Okay. Oh, love it. Okay, so it is currently not, but we're working on it. So initially the idea was to have, these linkages are very well fitted for having modular type checking. I think in the end, we ended up having some global reasoning about ancestors. So like I am a family, who are my ancestors, right? And that is a global function, but I believe that we can break it down into a compositional relation that will just be part of the linkage itself, and then the plus operation would take care of it by just concatenating these things. Yeah, thank you.
Yeah, thank you. Maybe just as a quick follow-up, I would be a bit concerned about modularity because you will need some form of coherence guarantee across all the board, and so that means that if you have two different nested families that decide to extend the same family, then you will get into trouble, right? So now you will need to get in sort of like orphan rule, Rust-like kind of system. So be on the lookout for that.
Okay, yeah, I will definitely be talking to you more about this. Thank you.
Okay, thank you again, Anastasia.
Thank you.
All right, everyone. Welcome to the last session of OOPSLA. We have a session entirely on effects, which is awesome because effects are hot right now, and there's so many discoveries and interesting applications. So I'm very excited. Our first talk will be on effect handlers for C via coroutines, and Mario Alvarez-Picalo will give the talk.
Thank you. Can I use this mic? Yeah, okay. Wonderful. Okay. Hi, everybody. My name's Mario, and I'm here to tell you about one of the many projects that are going on inside Huawei research concerning effect handlers. If I may, let me start this talk with a quote by Guy Steele. I'm not sure I'm senior enough to be the kind of person that starts talks with a quote by a famous computer scientist. But I quite like this one. We were not out to win over the Lisp programmers. We were after the C++ programmers. We managed to drag a lot of them about halfway to Lisp. And so this is partly as an excuse for perpetrating Java. Now I would like to start this talk with a slightly modified version of this quote. We're not out to win the Coca programmers. We're out to win the C++, or very specifically the C programmers. And we hope to manage to drag a lot of them halfway to Coca. The first question that you're forced to answer is, why would you do such a thing? Effect handlers, as many in the audience might already know, are an incredibly expressive programming language feature. They generalize stuff like green threads, actors, generators, exceptions. They can basically implement any sort of control flow that you want. And it turns out that there's only one programming language in common use today that lacks every single one of these features, and that's C. And so it stands to reason that C programmers have actually the most to gain from introducing effect handlers to C. But in a more practical sense, what happens at Huawei is that we have tons of people working on C, especially in embedded contexts. We have lots of people using C to write firmware for telephone switching hardware. We have lots of C that's running right now in data centers inside embedded devices. And one thing that happens a lot, and we actually see this a lot, is that there's a proliferation inside Huawei of concurrency libraries. It seems that every other team is reinventing their own library for green threads, or their own library for asynchronous tasks, or their own library for actors. And so we really wanted to find a single abstraction that unifies all of these things, that we can package as a library and give it to all of our embedded C programmers and tell them, look, here's the one thing you need. All of the stuff that you've been doing so far can be done in a much neater package with a much neater API with this library. And so the core audience of this library is C programmers, and specifically embedded C programmers, and that comes with a lot of very, very hard constraints. The first is whatever we come up with, whatever we give them, it has to be 100% compatible with the C programming conventions, and this, among other things, this means that, for example, we cannot move stacks around, which is, as we will see later, it's a common approach when implementing effect handlers, stack copying. This is completely out of the question because a lot of C programs depend on pointers into the stack remaining stable across function calls. They should also be ergonomic to use by hand, and C, unfortunately, is a very, very poor language. It has a very simple type system. It doesn't have polymorphism. Crucially, it doesn't have closures. And so it's really hard to give an API to effect handlers that doesn't depend on all of these things. So, as you may know, there are already a number of libraries that accomplish something similar, and they're truly excellent libraries. Both libhandler by Dan Lyon, who is in Microsoft Research, and libmprompt by Dan Lyon and Casey Sivaramakrishnan, who also give you an API from C to use effect handlers. However, the niche of those two libraries is vastly different because they're not meant to be used directly by C programmers. They were designed and developed as backends to the Coca programming language. So they're supposed to be consumed by a compiler, not by human programmers. And this comes across in the decisions that they make. So, for example, libhandler uses stack copying to manage resumptions, which is completely out of the question for C programmers because that's going to make half of their programs segfault. And libmprompt uses virtual memory for allocating growable stacks for your continuations. That's also out of the question because when you're working on an embedded system, you don't have an operating system, you don't have a notion of virtual memory. So we couldn't use any of these two libraries. And also, finally, and this is perhaps more of a sociological point, the APIs of both of these libraries actually are based on closures. So a handler is a closure. You handle code by bundling together a bunch of closures and executing them. And it turns out C doesn't have closures. So in order to use these libraries, you have to do a lot of closure conversion by hand. And this is not only really annoying, but it's also not type safe, and it turns out that you have to go through a lot of hoops if you want your handlers to capture mutable state. It's actually really a mess. And also, and this is a lot more subjective, we found that C programmers tend to get really, really scared when you say the word continuation. This is not a moot point. I've been in meetings where I've been told, if what you do it turns out to be equivalent to continuations, we are not using it. Continuations are this weird thing that Scheme has. Nobody knows how to program with continuations. Continuations are slow. We're not using that. And so what we decided to do is do a completely different API, a completely different reimagining of effects as something that we call handled coroutines. And the idea is you walk up to a C programmer and you tell them, I have a really nice coroutines library for you. And then you introduce, you can gradually introduce all of the cool advanced features of effect handlers as they become more comfortable with it. But crucially, if they only want to use it as a coroutine library, it is a very good coroutine library. It is really fast, it has 0 allocations, it cares about all of the things that C programmers care. And so we hope, and to an extent we have succeeded in smuggling effect handlers into the C community through the Trojan horse of coroutines. So what does this look like in practice? Here is a very simple, effectful program using libsef. First, you define your operations using this define effect macro, which takes the name of the operation, the return type of performing that operation, and any arguments that the operation may have. Ignore this number. It'll come back to haunt us later. And then, in order to use them in a program, you simply use the perform macro, and pass it the name of the operation, and any arguments. And this, you can tell your programmers, this is actually just like a function call. It's relatively type safe insofar as C is type safe, which is to say not very, but they're used to it. And so the argument types are checked, the return type of this is checked, and from the point of view of the programmer, this looks just like a function call. It may be able to suspend. That's the trick. So this is more or less what I said. Now, what is this number here? This is just a sad necessity of life. One of the limitations of libsef is the programmer needs to provide a numerical tag for each operation that they define. And we use this for very, very fast operation dispatch. But there are some limitations. You can only define at most 64 operations in any given program. And it is the programmer's responsibility to ensure that these tags are disjoint. We are working on lifting this restriction for a new release, but it's not super easy. There's something that I would like to point out here, which is not true in other libraries for effect handlers. Here, I have an effectful function that is stack allocating an array of length 256, and it is passing the address of that stack allocated array to an effect. The only reason this is possible to do is because our stacks are stable. We make you this promise. We never, ever, ever, ever move any memory on the stack, ever, under no circumstances. Crucially, libhandler doesn't provide this to you, so if you try to write the equivalent in libhandler, it will segfault your program, more or less immediately. So once you've defined your effectful code, how do you handle it? And this is the most important part. We don't really have a notion of handler. We have a notion of a coroutine. So in order to handle some effectful code, you need to turn the effectful function into a coroutine with the coroutine new function, which what it does is it allocates some stack space for that function to run, some metadata, and then you can immediately resume it using the aptly called resume function. Now, here comes the difference from normal coroutines. This resume function takes an extra argument, which is a bit set of all of the operations that can be handled by yielding to this context. Which is to say, whenever the code inside this coroutine performs any of the operations contained in this bit set, the code inside the coroutine will immediately yield as the return point of resume. At that point, you get a reified command. Unlike other systems, dispatching on what command has been performed is not done by the library. It is done by a standard switch statement. So you can switch on the effect tag of the request. We provide you with this convenient case effect macro, which does the matching and the unpacking of the arguments for you. And then you can just write your normal handling codes in completely indirect style. In something like libhandler or libemprompt, all of these handler branches would need to be manually closure converted code. And this is actually really bad because closure converted code in C++ cannot close over mutable variables unless you heap allocate stuff. And if you're not a C programmer, then you don't care about this. But if you're a C programmer, you really don't like to allocate at all. Now, returning, when the code inside the coroutine returns, this actually also behaves as if it were an effect. There's a different macro, case return, which handles the case where the coroutine is terminating. You have to manually delete that, of course, because this is C. We manage our own memory. And that's it. Crucially, this handler only handles the get and put effects that we've defined in the previous slide. We can separately define a similar handler loop to handle the print effect. And the code here is relatively straightforward. And then you can just compose them by composing closures. Unfortunately, some amount of closure conversion by hand is necessary because you need to initialize a coroutine, and initializing a coroutine requires you to create a closure. So at the end of the day, you can run this piece of effectful code by wrapping it in a closure and then wrapping it in another closure that runs the handler for state and passing that to the handler for print. Okay, so far so good. Here's some information that I don't want to spend too much time in this. This is just there for reference, but this is the entire API of the coroutine lifetime. You have your functions to create a coroutine, delete a coroutine, and a couple of functions to stack allocate coroutines if you're into that kind of thing. You can perform an effect, you can yield from a coroutine, and you can resume a coroutine with a set of effects that you're willing to handle. Crucially, coroutines are also thread safe, so you can pass coroutines across threads and start them in one thread, pause them, pass them to another thread, start them on that thread. And this is actually how we achieved a work stealing scheduler that I'll show you later. If you know anything about coroutines, you know that stack handling is pretty tricky. How we deal with it is we use segmented stacks. This is relatively straightforward because Clang and GCC these days have support for segmented stacks. And for those who don't know what a segmented stack is, instead of having a contiguous block of memory be your stack, you just have a linked list. And every time a function runs out of stack space, you allocate a new link, and you use that as your new stack. Stack handling suffers a potential performance problem called the hot split problem, which is when you have a tight inner loop that calls a function, and that function happens to require more stack memory than you need. So every time you call it, you allocate a new segment, and every time you return, you deallocate it. This is widely held to be a big problem. It's the reason why Go abandoned segmented stacks. It turns out to be not a big problem for us at all, because we found a relatively sensible way of solving this. When you return from a function that has allocated a new stack segment, instead of deallocating it immediately, you just leave it unused at the end of your linked list. And when you go back, when you call that function again, that segment is still allocated, and you can simply reuse it. And as you can see in this very nice graph, whenever your inner hot split function contains at least 10 multiplications, the overhead of this of hot split with stack-led recycling is basically negligible. And if your function contains fewer than 10 multiplications, then it's probably going to get inlined, and you're not going to have this problem at all. Finally, some benchmarks and comparisons with other effect-handled libraries. We install a stack of handlers up to depth k and perform 20 million commands. We've compared libsef with libhandler and libmpf. These are the two most important ones. As you can see, we are extremely competitive in the general case. If you opt into specific library-specific optimizations that you have to do by hand, then at lower depths, we are a little bit slower than libmpf and libhandler, but as you install more and more handlers, our much faster dispatch strategy tends to dominate, and we actually become much faster. We also built an asynchronous scheduler with work stealing, and used that to implement an HTTP server, mimicking the benchmark used by the OCaml effects paper. And it turns out, we actually found this quite surprising. Our scheduler is actually competitive with Hyper, which is fairly robust Rust HTTP server. So our performance tends to be really, really good, even if you just think of this as a pure coroutines library. So let me just finish with that. In conclusion, I think there's enormous potential for effects in C. They are, if you put them in the form of coroutines, they're really easy to explain to C programmers. They more or less immediately understand the underlying programming paradigm. And crucially, there's a lot of low-hanging fruit for compiler support, both in terms of increasing type safety and doing a lot more optimizations. And this can be done by simply tweaking a C compiler a little bit. We think we can achieve a lot of benefits in this area. Segmented stacks are a necessity, but it turns out they're not such a big price to pay. So in conclusion, I hope I can convince you that actually effect handlers in C not only is not a crazy idea, it may turn out to be a really good idea. And if you're interested in this at all, you can go to that GitHub address, download this, and start playing with it right now. Thank you very much, and I think I've run a bit over time, but if you have any questions, then...
So I was wondering, can you say a little bit about
okay. Yeah, so from the point of view, so we actually give you an API where you just don't see the effects at all. You have a fork function, you give it a closure and it runs it in a different thread. You have a yield function, and these are, from the point of view of the programmer, they are just regular functions. They just perform effects under the hood. And then you have a bunch of input-output operations that we provide to you as an input-output library, which are asynchronous. And underneath, they use a wait effect that basically tells the scheduler to block that thread until a certain condition is satisfied. So it actually looks a lot like a traditional async I/O with coroutines that you might have in a high-level language. You don't need to think about effects at all.
Super, thank you. So let's go. Yes, thank our speaker again. So the next paper in our sequence of effects is effects and co-effects in call by push value. The talk will be given by Manuel Suarez Acevedo.
Cool. Hey everyone, I'm Emmanuel. Feel free to call me Emma. This is work I was involved in while completing a master's at Penn. I am now a PhD student at Cornell. So let's talk about effects and co-effects in call by push value. To start off, I thought we'd have a motivating example. So for this bit of code here, we might ask ourselves, can the first line be removed as a compiler optimization, namely dead code elimination? And for this example, the answer is yes, right? We're not really doing anything in this first line. We're just binding the string hello to X, and we're not using X anywhere. So we can get rid of this line. This would be fine. We wouldn't be changing the behavior of the program. However, let's consider this slightly different program where we're saying let X be print hello. As a programmer, I'd probably expect this program to print hello and then print world. And if we were to get rid of this line, we'd actually be changing the behavior of the program. So although X isn't used anywhere, suddenly we can't actually kind of get rid of this line. And we can kind of ignore these two pieces and just sort of ask ourselves two questions to say, can we get rid of this line? The first one being, is the code bound to X pure, here E1? And the second one being, is X unused in the code that follows? So is E2 actually kind of using X? And because we're talking about a compiler optimization, our goal is to be able to track this statically at compile time. And for that, we're going to be looking at augmenting our type systems. So let's start with effects, considering now this different program where in this typing judgment where we have the program print X. And we're saying that it's well typed as long as X is of type string. And I threw in an extra Y in there because why not? And although we kind of have this idea that this program is well typed, there's this additional notion, right, that there's going to be some sort of output here. And this is information that we also want statically, right? There's a behavior that's observable. And for that, we might augment our type system with some sort of I/O effect information and say this program may have some sort of output effect. And really, we can kind of abstract this away to any structure that's an observable behavior. So now this program may have an effect phi, because we don't only want to talk about I/O effects, but also about running time, right? So how much time might this program take, or exceptions. And then on the other hand, we have coeffects. And if you've never heard this word before, anywhere that you see the word coeffects, you can kind of change it for demands, because that's really what a coeffect is the demands that a program is making on the world around it, and in particular on its inputs. So now let's kind of look at the inputs of this program. So the variable x and the variable y, we kind of are able to kind of talk about this relevance coeffect. So is this input relevant to my kind of program? And in particular, x is relevant because it's used, but y is irrelevant. And we could also augment our type system with this information statically, where we're saying, there should be a 1 in the x that isn't showing up there, but where we're saying that there's kind of this coeffect that we're demanding from x, and we're making no demands of y. And really, we can also kind of abstract this away again to say we're making some abstract demand q1 from x and some demand q2 from x2, because we want to talk about different coeffects. And before I kind of talk about those, we also can just extract all of these demands to just some sort of vector of demands, where now we're making demand qi on the variable xi of the context. And we do this because we don't only want to talk about relevance, but more generally we could talk about resources. So how many copies of a variable am I demanding? Or differential privacy. So how sensitive is a function going to be to its inputs? Or information flow, where I'm sort of demanding a confidentiality level to be respected by variables. And now, kind of revisiting this question from before, we can sort of identify these two questions as statically tracking the effect of E1 and the co-effect that E2 is kind of demanding of X. And there's kind of this one little bit here that's a little tricky, which is that question of statically tracking effects, right? So I've kind of ignored what programming language this is. Maybe you looked at it and thought it was OCaml. And if it were OCaml, we could ask ourselves, what's the expected effect of this program? And the answer would be that we run through this first line and we print hello, and then we bind x to unit, and we substitute x with unit. However, if maybe you like writing Haskell, then there's this kind of additional option here, where in the first line what we do is we take this line and we actually bind x to the code that says print hello, right? And in the second line, we instead substitute x with print hello twice and end up printing hello 2 times, and we'll have hello printed 2 times. I don't know why my slides aren't working super well, but the expected effect here would be hello twice. So instead of kind of having these questions of kind of what is the expected effect of the program, our goal is to instead use an intermediate representation, right? Because we're talking about compile time optimizations. And in particular, we want to be able to talk about both of these behaviors, right? Printing hello once or printing hello twice. But we also want this intermediate representation to have an explicit evaluation order, because we actually do want to have only one answer to the question, what is the expected effect of this program? And this brings us to call by push value, which is a programming language that has been referred to as a subsuming paradigm, because it allows us to talk about many behaviors at the same time, right? Both of these behaviors that I just went through, where we can take this program and we can translate it to call by push value so that we print hello once, or translate it to call by push value so that we print hello twice. And this has made call by push value a very nice intermediate representation, because it can talk about these behaviors while also being very explicit, because a nice thing about call by push value is that for both of these programs, there's only going to be one answer to the question, what is the expected effect? And the kind of the main idea behind call by push value is that it takes expressions and it splits them into values and computations. And Paul Blaine-Levy, who came up with call by push value, says that you can think of this as kind of a value is, so a string is a value, and a computation does. So printing a string is a computation. So to kind of go over what call by push value is in more detail, why not actually just take this program and translate it to call by push value two different ways, right? Print hello once and then print hello twice. So let's start out by printing hello once, where we take this first line and we translate it with this left arrow syntax, where this left arrow is sort of a sequence. And what the sequence operation does is it takes a computation of type funit, where f is this sort of returner type marker, saying that I will return a value of type unit. And the sequence operation binds the value returned by this computation to the variable x. And afterwards, we kind of keep on going with kind of the rest of our computation. And this is what a call by push value program is going to be in the end, is a lot of sequence computations. And the kind of remainder of our program is a translation of the next line. So kind of let's move on to that, where we're sequencing x with itself. So why not try sequencing x again using this sort of sequence operation. And there's this one issue here where x is a value. What we want to do is kind of add this syntax that says return x, so that we're saying take this value x and do the computation of just returning this value. And now we have a complete call by push value program, so we can ask ourselves what's the expected effect of this program. And if we run through it, in this first line, we're going to print hello and bind x to unit, and then substitute x with unit 2 times and complete our program. However, like I said, we can compile call by push value a different way, where now we want to print hello twice. So let's do that. We go through this first line and we use sequence again, but now we add this sort of kind of curly brace syntax, which means suspend, where I take this computation of type funit and I suspend it to this kind of suspender type marker that says this is a value of type UFUnit. And this is a value, so let's kind of say return this value. And now we kind of have this idea from before where we're saying I'm returning the code that says print hello. So moving on to the next line, we translate it with sequence again. And as before, x is a value, but really what x is a suspended computation. So we don't want to return it now. What we want to do is add this bang syntax that means force, that takes this suspended computation and forces it to be its underlying computation and actually kind of runs that computation. And now we have kind of we have a complete program again, so let's ask ourselves what the expected effect of the program is, where we run through this first line and we bind x to the code that prints hello that's been suspended. And the second line, we substitute it and we actually force this suspended computation. And then we print hello and return unit. And we end up doing the same thing in the third line, printing hello twice. And this is kind of the nice thing about call by push value, where we were able to translate this program two different ways and talk about these behaviors while still kind of having a very explicit answer to what is the expected effect of this program. So we don't try to kind of answer this question of dead co-elimination in this kind of random language. Instead, we talk about it in call by push value, where we take call by push value's type system and we annotate it with effects, where we kind of use this epsilon here to mean a pure effect. And this type system is very similar to kind of existing type and effect systems for call by push value. But what we do in our paper is we also annotate this type system with co-effects to ask ourselves, is there some demand being made on M? So is X unused in N? And this gives us this kind of new typing rule in our system that's kind of justifying this dead code elimination, where looking at this demand here, we see that it's ignored. So although M is demanding gamma 1, in our final conclusion, we actually can ignore the demand made by M because M is discardable. So we kind of take this this actual kind of code here and prove that it is in fact equal to N, which in practical terms tells us that for pure unused computations, it is in fact okay to kind of discard them, and dead co-elimination is correct. And this is a result that's been mechanized in Coq as well as have been the rest of our results in our paper. And we prove this equivalence with respect to the following semantics, where we take a computation in some environment, mapping variables to values, and we evaluate it to a terminal result, and we annotate it with an effect, which is the resulting effect from this program. And we annotate it with a co-effect, which is the consumed co-effects of the program. So this program will consume 5 resources, for example. And we take call by push values type system that we've annotated with effects, and we relate this type and effect system to our semantics, where we're kind of providing an upper bound to the effects that will happen at runtime. And it's an upper bound because we might have branching, and we might print in one branch but not print in the other. And we do the same thing for co-effects, where we also kind of say, that if we have a demand that we're making on M, that is enough. In fact, or those are the co-effects that will be consumed by the computation. And call by push value ends up being a really nice language to talk about effects and co-effects in particular, because it gives us this very clean separation. So, for example, we kind of are able to annotate our U types with effects, where this is the kind of suspended effect of a computation M. And we're able to annotate our F types with co-effects, where this is kind of the multiplied co-effect. So if V is demanding gamma, then if I use VQ times, for example, I need to multiply that demand by Q. And additionally, speaking of those compilations that I showed before, we prove that they preserve effects and that they preserve co-effects, kind of showing us that it's reasonable to talk about the effects and co-effects of a program in call by push value. And there's a lot more in our talk, but that's kind of some of the main ideas. And thank you very much for your time, and I'd be happy to take any of your questions.
Great. Questions? Yes.
What effect does adding the effects and co-effects have on the equational theory of call by push value? Do you have more equations or fewer?
Well, we don't really work with call by push values equational theory per se. We kind of work with our own semantics, so I can't really answer that question.
Maybe a follow-up to that. Excuse me. It looks like when you say that M sequenced with N is equal to N, that this is an equational. This is a kind of equational theory.
Yeah,
right?
yeah. I'm using this syntax to kind of as like syntactic sugar for saying that, and so we have kind of a semantics that we have in our paper, which is a semantics that actually discards unused computations, and we have a normal semantics which just says I'm going to actually not discard this computation, and we prove this result that basically both of these will result in the same value and have the same effect and have the same demands, the same co-effects. So that's kind of what this equivalence here means, just because it would be too much like different notation in one slide. Yeah. So the kind of equations that we do are with respect to this semantics here.
So I was a bit surprised about the semantics you say that the Haskell code has.
Yeah.
I don't think that's how Haskell works, right?
Yeah.
You're missing a do keyword or something.
Right. Yeah. I'm using Haskell as so really I'm talking about a call by name and a call by value semantics, but since I had like real code, just relating it to an actual language that sort of is call by name, but it isn't actually like good Haskell or correct Haskell code that you might write.
Well, Haskell wouldn't behave like that unless you put this statement in a do expression, right?
Right.
For the particular case of the IO monad.
Yeah, exactly. Yeah.
Okay. Maybe a more straightforward comparison could be made with Scala, where val binds call by value binding, whereas def binds call by name value. So you have both in the same language.
Yes. Yeah. I was looking for an example that would translate nicely to call by push value. That might have been a good one. Yeah.
Okay. Thanks.
I feel like this might actually be close if you interpret your semicolon kind of as a do.
Yeah, yeah.
That's how I looked at it.
Right. Yes. There's like, if you're thinking of it as Haskell, there's going to be like a do there, and you're going to use like Haskell's like sequence, like function that sequences like the monad.
Yeah, sequence is a different thing. If you use that, if you use sequence, then actually you get called by name, called by need. So you're not actually going to print twice.
That's fair. Yes. Okay. Yeah. Okay. Yeah. I mean, it's more the example to kind of just motivate that we have call by need semantics and call by value or in real languages. Yeah.
All right. Well, maybe the next speaker can come up while we take maybe one more question. There is one. So actually, one question I had was thinking about. So you talked about this theory and how you can use it to, for example, eliminate dead code. Do you envision that just as sort of underneath the hood in an ordinary in a programming language for within a procedure, or would you see this as something where you would add the types to the language to do reasoning across procedures and so on as well, and what might that look like? You have effects and co-effects in signatures then, right?
Right. Yeah. I'm not sure I understand the question entirely. Could you repeat it, maybe?
I'm just thinking about what. Have you thought about what this looks like in like a service language?
Yes. Right. So this is kind of a motivation, but we focus entirely on the meta theory, and some interesting future work would be kind of just an actual surface language that we're kind of elaborating into call by push value. Yeah. Is that?
Yeah.
Yeah.
Sure.
Cool.
All right. Thank you. Let's thank the speaker again. All right. The next talk in our session is lexical effect handlers directly. This will be presented by Kong Ma.
Hello, audiences. Today, I will show you our recent work on compilation of lexical effect handlers. This is a collaborative work with Zhao Yige, Edward Li, and Yizhou Zhang. Effect handler is a powerful language feature that allows programmers to write programs with interesting control flow. It subsumes many popular language constructs like async await, coroutine, and generator. The dynamically scoped effect handler suffers from a modularity problem, and there is a recent line of work that gives lexical semantics to effect handlers, which restores modularity to the program. Lexical effect handlers are expressive. They have been implemented in languages like Effect and Coca, and can be generalized to manage bidirectional control flows. Before we dive into details, let's first get ourselves comfortable with the operational semantics of lexical effect handlers. I'm going to show the source code on the left and the runtime turn on the right. As the control enters the handled body, we freshly generate the label 314, which is going to identify this handler instance. The label is also substituted into the handled body. Next, a raise expression is evaluated. The raise expression indicates which handler instance it raises to. The continuation is captured and is substituted into the handler implementation for K. Finally, we reduced a resume expression. The first argument is a continuation, and the second argument is a value. After the reduction, the whole of the continuation is filled with the given value. And that concludes the demonstration. The lexical effect handlers, being an attractive language feature, still doesn't have an efficient implementation. As you will see shortly, the current implementation suffers from a scalability issue. The program on the left is something that could be written by a real-world programmer. It shows a recursive function where the body of the function is wrapped inside an exception handler. The function can also raise a logging effect, as is indicated by the function signature. Effect with a K is a state-of-art language with lexical effect handler. If we run the program without the logging effect, this is what the running time looks like. The x-axis is a plot in the input size, which corresponds to depth of recursion, and the y-axis is the running time. If we turn on logging, the running time becomes the line in red, it shows a polynomial scaling trend, which is not ideal. In this work, we implement a compiler for our language Laxa. We're able to achieve linear scaling trend with or without the logging effect. For this particular program, Laxa also runs a lot faster compared to effect if you look at the y-axis. However, we want you to only pay attention to the scaling trend, as the scaling trend manifests the difference in our compilation strategy, which is the focus of this talk. In this work, we show how to compile high-level modular algebraic effect in Laxa to low-level swift stack switching in assembly. Our system finds the handler in constant time and captures the continuation in constant time. We thus claim to be more scalable than existing solutions. To understand why there is a scalability issue with existing compilers, let's see the concrete execution of this program. I will illustrate the evaluation context on the right as the program runs. Before we enter the function, there is already a logging handler installed on the evaluation context with a freshly generated label 123. As the program runs, we install a sequence of exception handlers on the evaluation context. When an effect is raised, the operational semantics indicates that the closest enclosing handler that matches the label 123 is used to handle the effect. Finding such handler requires a linear search of the evaluation context, which is costly and is a source of the scalability issue that we just saw. There are compilation strategies that avoid the use of labels, but it still exhibits a searching behavior similar to this one. Searching for handlers seems to be at odds with the spirit of lexicoscoping. Lexicoscoping is all about statistical reasoning. It's about knowing things at the compile time. Searching for the lexical handler at the runtime feels unsatisfactory. This unsatisfaction is resolved when we compile to low-level languages. We no longer need labels. Instead, every handlers naturally have a memory address, which we use to identify handler instances. Consequently, we can reach a handler in constant time. To see how we apply that insight in practice, I will show you how we compile the effect handler constructs into assembly sequences that manipulate stacks. First, let's look at a function without effects, just to get you comfortable with the animation that I will use throughout the presentation. This function in Laxa simply performs addition. The function is compiled to the assembly sequences on the left. We will see an illustration of stack in the middle and the register files on the right. As we enter the function, the arguments have been pushed onto the stack. We now execute the instruction highlighted in yellow. The red arrow indicates the position of the stack pointer. The stack grows downwards from bottom to top. First, the addition operands are loaded into register R1 and R2. An addition is performed with the result stored in R1. Then, to translate the light binding, the result of the addition 43 is pushed onto the stack. We then load the 43 back into the register R1 as the final value of the function. After that, the stack is popped, and the return instruction is executed with the return value in R1. Now let's look at an Laxa expression that uses all effect handler constructs. The compiler provides 3 built-in assembly instruction sequences that could be called from other places. We will show their implementation later. Let's first look at the compilation of the handled body. Among them is a raise expression, which is compiled into 3 lines of code. The handler reference is moved into R1. The argument, a unit, is moved into R2, and a call to raise instruction sequence is made. The resume expression is compiled in a similar way. The entire handle expression is compiled into 3 instructions. The code location of the handler and the handled body are moved to R1 and R2, and a call to enter is made. Starting from this point on, let's see the actual execution of the program. The control is now inside the instruction sequence enter. You don't need to pay attention to the assembly sequences. The animation is sufficient to understand what's going on. We first allocate a new stack using the assembly instruction make stack. We then push the handler function onto the stack. And then we push the pointer to the top of the previous stack. We will call the first two slots of the stack the header frame of the handler. They include necessary information for the handler to carry out operations. Finally, the control goes to the handler body. The only argument of the function, which is a pointer to the header frame, has been pushed to the stack. This value is going to be passed down to the call chain to every function that will potentially raise to this handler. The control is then transferred to the body function. Now we're inside the body function, and say that we are raising to the handler that we just installed. As the semantics dictate, we're going to capture and reify the continuation. This is done by the first part of the raise instruction sequence, which perform an exchange between the stack pointer and the header frame. Now the header frame no longer points to the previous stack. Instead, it points to the end of the resumption, which in this case is the top of the current stack. We then malloc a single element tuple to store the pointer to the header frame. This single element tuple will be used to represent resumption. We use this in direction so that we have a way to invalidate the resumption after it is used. Although our formalism only supports single-shot resumption, our compiler implementation supports a limited form of multi-shot resumption. Finally, we are ready to jump to the handler implementation. R1 stores the first argument, a unit, and R2 stores the second argument, which is the resumption. R4 is the jump target. Now the control is inside the handler. Let's say that we are at the beginning of the resume instruction sequence, which is going to resume the resumption. At this point, R1 stores the argument to the resumption, and R2 stores the resumption. We first load the pointer to the header frame into R3. And then we override the single element tuple with a special token to prevent the resumption from being used again. Next, we perform an exchange between the stack pointer and the header frame. The stacks are, in a sense, linked again. With an execution of the return instruction, the control goes to the top of the resumption stack, effectively resuming the computation. As you may have noticed, the handler in this program resumed the resumption in tail position. This means that resumption is not used in any interesting way. Consequently, we don't need to allocate a new stack when we enter the handler construct. The Lexa compiler will instead allocate the handler's header frame within the same stack, saving an allocation. Lexa compiler carries out the same optimization for abortive handlers, which are handlers that do not use resumption at all. We formalize the operational semantics of the source and target language and prove that compilation is semantic preserving. The proof uses a canonical simulation argument. You can find more details in the paper. On this page, you see the architecture of Lexa compiler. The Lexa source code is first compiled to C, then combined with assembly sequences that you just saw. The program is linked to a garbage collector and sent to LLVM for optimization and native compilation. Please check our paper for discussion on implementation techniques. In particular, there is a discussion on using calling convention instead of using set jump, long jump, and consequently allowing the compiler to do more optimizations. We evaluate Lexa on a set of community-maintained benchmarks. We also added a few benchmarks that represent the real-world use of effect handlers. In the next few slides, I will share with you interesting findings using a few scaling plots. Iterator is a simple program that uses a handler in a tail resumptive way. The Lexa running time looks flat because it is indeed flat. The Lexa compiler compiles program to a constant. This is in part thanks to the optimization done by LLVM, but it also shows the quality of code generated from Lexa. Resume non-tail2 is an artificial benchmark that checks how efficient a language captures continuation. The plots are split into two for easier visual comparison. Coca has a polynomial runtime trend because it builds continuation frame by frame. OCaml is stepwise linear because it copies and doubles the stack upon overflow. Effect compiles by CPS, so no extra effort is needed to capture continuation. Laksa uses segmented stacks, so also no extra effort is required to capture continuation. Interruptible iterator is adapted from previous work. It allows the client code of a coroutine iterator to concurrently update a list during iteration. The program installs deeply nested effect handlers, similar to the one we saw before. Effect has a polynomial scaling trend, as it performs a linear search on every race. OCaml also has a linear trend, as it also performs linear search on every race, as it's dictated by the semantics of dynamically scoped handlers. Coca avoids linear search with tail resumptive optimization. Laksa achieves linear scaling because it raises effect in constant time. I hope you enjoyed this talk. Laksa compiler is open source. It is still in the early stages, and we're adding exciting new features. So expect to see more Laksa talks in the future. Thank you.
So we have time for some questions. I will start with one. Can you talk about, so first of all, this is really cool. It's great to see excellent performance. I guess the second result in this sequence talking about performance. And especially with the challenging semantics here. But one of the, I was curious about the limitations with multi-shot, right? So under what circumstances can you support multi-shot continuations?
Yeah, great question. So the difficulty of supporting multi-shot resumption is that we basically pass down a pointer to the header frame down the stack, right? So that's a pointer into the stack. And when you copy the stack, you copy the old pointers. So that results in a sharing of the header frame of the handler. And consequently, we have a limitation of you can only resume one copy of a resumption at a time. You can't have two active resumptions at the same time because that will result in sharing and each invalidating each other's header frame.
I see. Is that something that can be checked in a discipline by the parser or by a type checker, or is that something the programmer has to follow?
Yeah, it's something that programmers has to follow. This work doesn't have a type system. It's about compilations.
Sure.
So, sorry.
Future work, perhaps.
Yes.
Yeah, interesting.
Sorry if this is a silly question, but just to follow up on that, does that mean that in principle, or rather in the language, it does not restrict the use in multi-shot contexts, but it is the programmer's responsibility to ensure that the shots don't occur at the same time to avoid like undefined behavior or something?
Yeah, basically our source code will get stuck if you reduce resumption twice, right? So yeah, if you do that, your program will get stuck or go into undefined behavior. We prove our simulation based on that, right? If your source program, doesn't get stuck, the targeted program also doesn't get stuck.
Thanks.
Okay, thanks for the talk. I agree with you that this is the way lexical effect handlers should work, and I think this is the way effect handlers should work. We shouldn't use dynamic scoping, right? This is
great.
Something we learned from history. But I'm a bit concerned about the multi-shot thing. So can't you at least check at runtime that this does not happen? We don't want undefined behavior, right?
Well, yeah. There's actually I should say that as it probably illustrated in the animation, we override that single element tuple with a token, right? So we could just let the compiler, abort if they see that token.
Yeah.
But yeah, it's a small change. I think we can easily implement that.
Okay, so that's good to know.
Mm-hmm. Thanks.
Well, if there are no more questions, let's thank the speaker. Okay, and this is an online talk. Excellent. For the last talk of the session, we have higher order model checking of effect handling programs with answer type modification, and Taro Sekiyama will be giving the talk.
All right, thanks for the introduction. So I'm Taro Sekiyama, and this is a joint work with Hiroshi Uno. I think he would be in the venue. And this talk is about high order model checking for programs with algebraic effect handlers. So the model checking is one of the most successful verification methodologies, and it takes two inputs. The first input is systems, which may be programs, graphs, or state transition systems. And the second input is properties, which can be expressed as temporal logical formulas or automata, usually. The model checking problem is to decide whether the system M satisfies the desired properties phi. The higher order model checking is an extension over model checking to higher order programs. So here the systems is represented by the higher order program that yield possibly infinite trees. So systems may be higher order recursion schemes or PCF terms. And the properties is a predicate over infinite trees, and which can be expressed as some logical formulas or tree automata. And the higher order model checking problem is to decide that trees generated by the system M satisfy the desired properties. And it can encode many kinds of verification problems, including safety and liveness verification problems, such as assertion checking and termination or non-termination analysis. One of the advantages of the higher order model checking is that it is decidable if the data domains are restricted to be finite. But to apply the higher order model checking to real-world software systems, it would be desired to support the effectful programs. Actually, so far, there are several studies to support the effect, such as non-deterministic choice, exception handling, and resource handling, such as files. But there are more effects not supported yet. For example, mutable store, IO effect, backtracking, correlation, and so on. So it is desired to develop a general framework that can support these more effects. At this year's proposal, Rago and Guilhem presented extensions of higher order model checking to algebraic effect and effect handlers. And algebraic effect are mathematical abstractions, and they can express many kinds of effect, like the global store, IO effect, and non-deterministic choice. And effect handlers can provide the ability to access the delimited continuations with the user. And the abilities makes it possible to express a continuation-based effect, like the exception handling, or local store, and backtracking, and corruption, and so on. But the problem is that the higher order model checkings for effect handlers is undecidable. This is because effect handlers can encode natural numbers, and the higher order model checking problems with infinite data domains, like the natural numbers, is undecidable. But this is not the end of the story. A natural question is that what fragment where higher order model checking is decidable? And we tackle these questions. And in this work, we identified a rich class of higher order programs with effect handlers, where higher order model checking is decidable, and effect handlers are still expressive enough to implement many kinds of effect. Our key idea for that restriction is to restrict the use over delimited continuations, and we use answer types and answer type modification to implement the restriction. And we also defined shape-based transformations, which can remove effect handlers, and we use the shape-based transformation to prove the soundness of the higher order model checking for the identified fragment. And we also use shape-based transformation to implement model checker for higher order programs with effect handlers. But I will skip the implementation part in this talk. Okay, this is a summary of our work. So from now, I will explain the more details about our work, but before that, I want to explain more about the background. So the higher order model checking for effect handlers are studied by the Rago and Guillem, and they target the language called HEPCF. This language supports higher order functions, fixed point combinators, and finite data domains like Booleans, and effect operations and handlers. And in this language, effect operations is described like this one. Here, this is a call of operation OP, which takes the argument value P. And M represents continuations of this operation call. And X represents the result of the operation call. And M can reference the result using the variable X. And if the operation is called in some context, then the operation bubbles up using the first reduction rule. It means that if the continuations of the operation call is M2, it is pushed into the continuation part of the operations like this one. And the operation is handled by the effect handlers, and to make the handlers activate, to make the handlers active, we can use the with handle construct, this one. And here I suppose the operation OP is called, and H provides some implementations of the called operations, which is named M prime here. And then the operation implementations of operation OP provided by the H is executed. But here, M prime may contain the free variables X and K, which represents argument and continuations of the operations. So these variables are replaced by the corresponding values. Okay, and so then actually using a variable K, M prime can access to the delimited continuations. Okay, but this is a reduction semantics, but to formulate a higher order model checking, the previous work also defines tree semantics. In the tree semantics, programs generate trees called effect trees. So let's see one examples. So this is in this term, the three operations are called ask, tell, and raise. So here, from this program, we can generate effect trees like this one. Here, nodes are labeled with operations used in the original program. So because in the original program, the operation first invoked operation is that ask. So then the root node of the effect trees is labeled with ask. And in the tree semantics, handlers carry out folding over effect trees. And the handled effect do not appear in the generated effect trees, and only unhandled operations may appear in the trees. So in these examples, the operations tell is handled by some effect handler. So then in the generated effect trees, tell does not appear. But the other operations, ask and raise, can appear because it is not handled in the original programs. Okay, and using this tree semantics, we can formulate the higher order model checking for effect handlers. In the model checkings, first we generate the effect trees from the given programs. Then we can check that the generated tree satisfies given desired properties. But for example, the property can state that no raise operation is called in the program. But as I said, this model checking problem is undecidable, at least if the phi is expressed as MSO formulas, because effect handlers can encode natural numbers. Okay, and to see the problems, let me re-examine the encoding over natural number proposed by the previous work. And the point is that natural number n is encoded using the other n calls to some specific operation stuck here. And the case split on natural numbers can be encoded using the effect handlers. Okay, and using this encoding, for example, we can implement basic arithmetic operations, especially the subtraction v minus n can be implemented using n effect handlers. Okay, this is a problematic encoding, and we want to reject the program in using this kind of encoding. So our key idea to prevent the natural number encoding is to bound the number over simultaneously active effect handlers. So okay, so let's see what it means. So more formally, this restriction can be stated like this one. So here, E is a term to be model checked. Then there exists some natural number n that bounds a number over effect handler that appears at runtime and simultaneously handles the effect of some term E prime here. And active effect handlers means that effect handlers in the state of obeying the effect of some term. Okay, so then why does this restriction prevent the encoding? So to see it, first, please remember that the predecessor over natural numbers is implemented by effect handlers like this one. And by bounding the number over simultaneously active effect handlers, we can bound the number of applications of the predecessor. So then, as a result, we can bound the range of the accessible natural numbers by imposing the restriction. It means that under the restrictions, we cannot access the unarbitrary natural number. So then it means that the natural numbers cannot be encoded completely. Okay, so this is the basic ideas of our restrictions, and but the next question is that how we can enforce such restrictions. Our approach to implementing the restriction is to introduce a type system with answer types. And answer types are types over delimited continuations. And the distinguished point for our work is that answer types can reveal the number over delimited continuation necessary to evaluate terms. And the number over delimited continuations correspond to the number over effect handler that can be active at the same time. So by bounding the size over answer types, we can bound the number over simultaneously active effect handlers. So this is ideas why the answer types can work to implement the restriction. Okay, and this is a type language in our type system. The most important gradient is that computation types here, and the sigma is operation signature, but it's not important. So here, so let me omit it. And T is a value types, which represent what values are produced by the terms of these computation types. As remaining two types is answer types, and which are either over value type or computation type. And the first answer types is called initial answer type, which represents the return type of the delimited continuation enclosing the terms of this computation type. And the second answer type is called final answer types, which represents what the meta context expects for terms. And meta context is a context that enclosing the delimited continuations. Okay, So maybe for someone familiar with the CPS transformations, one way to understand this type of language is to check the CPS interpretations. So this is our CPS interpretations for the computation types. Here we can find that the T1 value type T1 and initial answer type A1 can make the type over continuations. And then the meta context can provide the continuation of this type, and then you can get the result of the type A2, final answer type. Okay, and in our type language, computation types can take this form in general. Here, which consists of the n pairs of value types and initial answer types, and then it ends with some value type. Then the CPS interpretations of these computation types can be given like this one. And it means that the computation types can take only the n continuations. So then it means that the number of continuation passed to the terms is bounded statically. So this is why the answer types may work, can work for the implementing the restriction. Okay, and the result is that we can show that the model checking for higher order programs with effect handlers is decidable if the program is well typed in our type system. We prove it using the CPS transformations, but I will skip the details in this talk. So please check out our paper if you are interested in the detail. And we also confirmed that our type system can accept many effect handlers, like the exception handling, local store, backtracking, and so on. This is because our type system restricts the use of effect handlers, but not the effect handlers themselves. So then our type system can accommodate many kinds of effect handlers. Okay, let me conclude. So we show that the higher order model checking for effect handlers can be made decidable using answer types. And our work is one example that shows that answer types are an effective tool in reasoning about effect handling programs. Yeah, that's it. Thanks for listening.
Great. Do we have some questions? Yes.
Yeah, did you do any examples of things that are checkable? Like, did you get some benchmarks on it? I'm just curious if it actually worked in practice, given the restrictions you put on it.
Yeah, and we use the examples with local store and exception raising operations, but it is still a small examples and small specifications. So the experimental result is promising, but we don't test it in the bigger examples.
Can you think of your can you think of your approach as having some relationship to bounded model checking?
Oh.
It seems like you're using answer types to put a bound on the search space that maybe is similar to what bounded model checkers do.
Yeah. Right. Okay, that sounds interesting questions. So I have no concrete answers, but it might be possible to formulate our idea as a bounded model checking extended for the higher order model checking, higher order programs. Yeah, that may be an interesting questions, but I'm not sure the answer.
Sure. Okay. So another question, I guess, maybe this follows up on the earlier one, but is there any prior experience with? I'm not familiar with answer types myself. Is there prior experience with kind of how restrictive these are on programs? I'm wondering, what are there kinds of program uses that are likely to be prohibited by this, and are there Are there conversely classes that are likely to be fine?
All right. So yes. So maybe one of the problem is that it's related to the restriction proposed in the this type system. So one thing is that answer types can bound the number of effect handlers. So it means that we need to constrain the constrain the number of effect handlers used at runtime. So I'm not sure it is okay. So it may be problematic in considering the modular verification because we need to know the what number of effect handlers are used before model checking, right? So then it might be difficult to verify the programs in modular way in the presence of the answer type modifications. It's one of the critical problems, I think.
Okay, yeah. So I imagine something like exceptions. You're typically not throwing lots of exceptions in a program, so I would expect that to be bounded. But I wonder, like another use of effects is for something like coroutines, like yielding things, and maybe if you don't have a bounded data structure, would that be an example of something that would be hard to type with answer types?
Right. I think actually we are considering the application in such a context. So maybe a concurrency or user level thread scheduling. Yeah, I think it's a promising direction for future work.
Yeah. Okay. Good. Any final questions? If not, then let's thank the speaker again.
Thank you.